Good morning, everyone. While the last few people trickle in, it's a little after 9, so I think it's time to start the session. My name is Inge Loes ten Kate. This is my first Rocky Worlds, and I'm highly enjoying myself. So it's a really nice conference. And thank you all for... This one is real. Okay, we start today with a keynote, then followed by 4 other speakers. Thank you for being here all after the, I think, eventful karaoke night. So I think it's time to start. And with this, I would like to introduce Lena Noack from Vrije Universiteit in Berlin. And she will kick off today with a talk about planetary habitability and atmospheric diversity.
Yeah, thanks so much for the introduction, for inviting me here. It was really a pleasure to be here at the Rocky Worlds conference, and I'm absolutely amazed how many people are in the room at this time. I was guessing about 10 or so would maybe make it at this morning. Yeah, so I will talk a little bit about how we can actually predict, on the one hand, if a place might be more interesting when it comes for searching for biosignatures later on. So which planet may be more interesting for habitability or less interesting for habitability. And specifically, what kind of atmospheres would we actually expect on such a potentially habitable planet? And what should we exactly look for? So, of course, when we come to the question of astrobiology, exoplanets, the first question is what matters for habitability? And there are different kind of things that we have to take into account. So it's not an easy problem. We have to look at what kind of outgassing from the interior you would expect if you're talking about surface habitability. We have to look at, is there still a primordial atmosphere around or not? Then how strong is the atmospheric erosion that we're expecting? What is actually the composition of the planet? We had a couple of very nice talks about this week. Impacts, they can either contribute, if it's cometary impacts with delivering volatiles, or erode the atmosphere. We also heard a little bit about this beforehand. How is the interior actually made up? Interior structure was also something covered here. Star-planet interactions in general, of course, are very important. Cosmic radiation, especially if we talk about habitability at the surface of a planet, then radiation becomes a very important factor. And therefore also, how does the interior actually influence surface habitability? So heat production in the interior is important. Potentially induction heating from, again, there's a star-planet interaction that we have to look at. Magnetic field generation to shield the surface from cosmic radiation. Tidal locking is also one of the factors influencing habitability. Climate, how does it actually evolve over time, and so on, and so on, and so on. So you see that almost all talks that we actually heard this week fit into the topic of can a planet be habitable, or what kind of atmospheres would we expect there actually. The 2 factors that I would focus on more is the interior dynamics, and how does interior dynamics contribute to at least some of these factors. Don't worry, I'm not talking about all of these. And the redox states that we also heard quite a lot about already. How does this influence then the atmosphere that we expect in the end? So I hope by this overview I've already convinced you that the interior really matters for surface habitability. So on the one hand, the main key contributions also from the dynamics of the interior is a question, can we have a magnetic field? Can we maintain a magnetic field over long time scales? On which planets would we rather expect a magnetic field than on other planets? By the way, magnetic field is maybe not so much important for atmospheric erosion, because depending on what kind of process actually erodes an atmosphere, and magnetic field can help, can not matter at all, or can even harm atmospheric erosion. But for shielding life at the surface from cosmic radiation, there a magnetic field is quite important. Then the thermal evolution, of course, drives all these different things that we see at the surface processes, plate tectonics, volcanism, outgassing, and so on. And the interior chemistry, as we already heard also in the talk from Emma, is what really drives what kind of atmospheres we would actually see at the surface. So in the next 25 minutes, I will talk about two topics. One is which worlds should actually potentially be habitable, and then the main part will be what kind of atmospheres would we then actually expect on these worlds. So the first thing that I would like to point out, maybe everyone in the room is aware of it, but when I started my PhD, I was not aware of it really. When we think about a habitable world, we typically think about an Earth-like planet. We think about oxygen in the atmosphere. But actually, when it comes to the origin of life, at least origin of somewhat Earth-like life using amino acids, proteins, and so on, then oxygen is actually quite harmful. And for the actual origin of life, reducing conditions are actually extremely favorable for prebiotic chemistry. There are also other ways around it, but if you're looking for the most likely habitable planet, reducing conditions will actually be in favor for the origin of life. But if you look at what happened on Earth, I mean, we know we had a great oxidation event, there was more and more oxygen building up thanks to life, in the case of Earth at least. And this actually allowed life to become macroscopic. So we can actually see how life, the mass of life, so the body volume changed more or less at the same time as the amount of oxygen in the atmosphere increased, because this is actually very good energy donor for life to actually be able to have a macroscopic form. The cells can actually have different functions because not everything is for energy production anymore. So for life as we are right now, and I don't necessarily mean humans, it could also be trees or something like this, oxygen is actually very favorable. So what we're looking for is a planet somehow in the sweet spot in between, right? A planet that might have had reducing conditions somewhere in the beginning, but has a potential to become oxidized over time. A planet that is oxidized already from the beginning, at least for the origin of life, might not be that interesting. So somehow this is something related to maybe also what the interior, how the interior drives the atmosphere, and specifically the redox state of the planet, of the system, matters quite a lot. So again, as I'm talking only about surface habitability here, we have to wonder first about the availability of an atmosphere. And where would we expect an atmosphere? And we have seen quite a lot of these figures in this week already from the cosmic shoreline. You can imagine your most favorite picture here instead of this one. They all tell more or less the same story. One version of the figures that I like quite a lot is from the paper from Dawn and Heng. The x-axis are a little bit different than you may used to with the typical cosmic shoreline picture. But what this one actually points out, maybe it's clear to everyone, but if we actually find planets in this region where we would expect strong atmospheric erosion, then there has to be some kind of secondary atmosphere. So actually we can turn this picture of the cosmic shoreline also around. If you want to get a better understanding of production of an atmosphere, maintenance of an atmosphere, this is a much more interesting region. Whereas down here, depending on the strength of atmospheric escape, depending on the type of atmosphere we have, for planets that have a couple of Earth masses, they may actually have very dense primordial atmospheres or atmospheres left over from the magma ocean stage and may then not be habitable at all and not interesting for life, as we know it. So how do we produce a secondary atmosphere? We can do numerical models and try to understand how the dynamics of the interior of such a rocky body actually leads to building up an atmosphere. And this is a standard simulation for a somewhat Earth-like planet without plate tectonics, so having a so-called stagnant lid at the surface. And what happens here is, what you see is an initially more or less wet mantle left over from the magma ocean stage, becomes over time drier and drier. Why does it happen? Because we produce melt, and water preferentially goes from the solid matrix into the melt. The melt, if it can rise actually to the surface, will then actually take the water out and we build up an atmosphere. But this also means the interior becomes depleted over time and volatiles. So this kind of melt doesn't happen everywhere in the mantle. This kind of melting process is typically limited to very shallow regions, at least melts that can really then rise to the surface and contribute to outgassing. And this is depicted here on the right side, where you can see different kind of melting temperatures, and in red, a typical temperature profile like we would expect for such a planet. And what you see is, in the first thing, that melt is the temperature in the mantle typically increases much stronger with pressure than the melting temperature. So usually, once we are actually after the magma ocean stage, the region where we can have melt is quite limited. Second, what actually happens is that if melt is actually produced further down, like the basal magma ocean, for example, that we've talked about, it will be so strongly compressed, it will be much denser than the surrounding mantle, that it will actually remain in the mantle. So even if you produce melt, it doesn't automatically mean that it lands at the surface. And so the region where we can actually have melt that produces an atmosphere is quite a shallow region. This leads to something that Paul also pointed out when he was commenting on his poster, that there is a sweet spot somehow for planets of having strong volcanic outgassing. So we have here a summary of a couple of models with different factors that we vary. It doesn't matter what the details are. Doesn't matter what exactly is here written on the y-axis. What matters is that if you have a very small planet, like a moon-sized planet or even a Mars-sized planet, even if it's volatile rich, what we would call volatile rich, the atmosphere that we would form would still be a very thin atmosphere. So Mars would never be able to generate a Venus-like 90 bar CO2 atmosphere because of the small mass, because of gravity influencing atmospheric pressures. If you increase the planetary mass, then if you have strong volcanic outgassing, if the dynamics of the interior allows for efficient volcanic activity, we produce more and more volcanic outgassing, more and more atmospheres. This means like a sum of total outgassing. It doesn't mean that this is exactly the atmosphere what we would have. But if we go to more and more massive planets, then this region where we can actually have melt in a stagnant lit planet becomes thinner and thinner. And this is what actually may limit volcanic activity if we go to larger and larger masses, depending on our assumption on rheology, temperature, and so on. But there seems to be, at least for stagnant planets, some kind of a sweet spot of where volcanic activity could actually happen. And a couple of years ago, we summarized this in a mass radius diagram. So this is a range of what could be, in principle, a rocky planet made of either very small cores or up to very large cores. And in green is a region where we would predict sufficient outgassing to actually maintain a dense enough atmosphere, even if you had atmospheric erosion, that our standard habitable zone concept actually works. Because if we want to have span the entire region of the habitable zone with an Earth-like planet, we go further away from the star, we need to be able to actually produce enough CO2 to actually still have a strong enough greenhouse effect. And we then have regions, if we go to more and more massive planets, again, depending on our parameters, where this may just not be justified, and our classical habitable zone concept may just not work anymore. But in this model, there are quite a lot of caveats. One was already pointed out before, shown in the paper from Caroline Dorn and Kevin Heng. What about the leftover primary atmosphere? So planets in this region, if they have an atmosphere, they probably have an extremely dense and uninhabitable atmosphere. Or if they have strong erosion, they may have no atmosphere at all. So it's very difficult in this mass regime to somehow be at a sweet spot where you have just the right 1 bar, 2 bar, 3 bar, maybe nitrogen or CO2 atmosphere. So therefore, the smaller masses may be more favorable for habitability, at least for stagnant planets, because of course we could also have plate tectonics. And there may also be delivery of cometary material, which here we didn't take into account. But why does plate tectonics change the thing? Well, if you go to plate tectonics, then this figure you've also seen before this week already. As I said, in the stagnant case, you do have this thick stagnant layer on top, which is immobile, and melting would need to actually happen underneath. And we only have this very limited pressure range where we can actually have melt. We produce that, and it's actually able to outgas. And if you have plate tectonics, then by having plate tectonics, we actually have ridges where hot mantle material goes close to the surface, melts, pressure release melting. And so if we actually have plate tectonics, then having a volcanic activity would actually be no problem at all. And indeed, if you look at the amount of volatiles that can survive in the interior after several billion of years for like a 1 Earth mass planet or 10 Earth mass planet, blue against that's for water-rich material that we actually start with, and red stats for dry material. So this means this material is now actually in the atmosphere or was outgassed. We can see in this mobile or plate tectonics regime, we really so small as the entire mantle and get the volatiles out. So we can actually have a lot of outgassing, even for this 10 Earth mass planet. Whereas in the stagnant lit case here on the right side, at least for the massive planets, there's only very limited outgassing possible. And we see a quite clear trend how this evolves. And again, I point out to Paul's poster for more information on that. So if you have plate tectonics, there is no limitation to the greenhouse effect. And then, of course, the main question is, what does plate tectonics actually depend on? Is it more likely or less likely with planetary masses? And you've seen this figure also before, summarizing that many different studies get many different ideas of how the likelihood of plate tectonics changes with increasing or even decreasing mass. They don't contradict each other. It just looks like it, because it's a multi-dimensional figure with a lot of different parameters on the x-axis, and depending on what you concentrate on, what parameters you choose, either plate tectonics becomes more or less likely with increasing mass. So currently we cannot, I would say we cannot predict which exoplanet can have plate tectonics or not, because it depends on so many factors that we cannot observe, that indeed if it comes to planetary habitability, which are the most interesting bodies to look at, are these planets of maybe 1 to 3 Earth masses where we don't necessarily need plate tectonics to maintain a strong enough greenhouse atmosphere that would allow for liquid water at the surface at the right distances from the star. And of course, there's also this other factor of the question of the magnetic field, also the length of a magnetic field that you can actually maintain again for a stagnant lit planet, because this is the maybe most common scenario of planets that we have out there. We also see here a sweet spot of planets somewhere rather getting close to the 2 Earth masses that may allow for a longer time for magnetic field to shield potential life at the surface. So this may be the sweet spot for habitability. So coming then to the second part, which atmosphere would we now actually expect for these planets? And there we have to look at what kind of evolution or what kind of step of an atmospheric evolution do we actually look at. And here you can see a sketch of how our own planet Earth actually evolved over time from the magma ocean stage core formation to the long-term evolution and when actually life started to change the atmosphere. And so indeed, for the more massive planets, signatures from the primordial or primary outgassed magma ocean atmosphere will survive. But if you go to these about 1 or 2 Earth mass planets, then maybe secondary outgassing is the main factor contributing to shaping the atmosphere. So in the rest of the slides, I will only concentrate on the secondary outgassed volcanic atmospheres and how they could actually look like. There have been a couple of studies looking at this. This is only a subset, so please excuse me if your study is not here. I know there are many more. But you can see that a lot of people have looked in the recent years, specifically depending on the oxygen fugacity or this redox state, what kind of atmospheres would we actually expect? And there are some similarities that, yeah, if you have reducing conditions, we would expect reducing atmospheres. If you have oxidizing conditions, we would expect like CO2 or maybe water-rich atmospheres. But still, all of these studies are a little bit different, specifically for questions about carbon or sulfur species and so on. So let's have a look at what are the key processes that actually influence secondary atmospheres and see what would then come out as potential atmospheres that we can expect for different planets. So the first factor that all of the studies typically take into account is, on the one hand, that depending on this redox state, we have a speciation of gases that favor, depending on if you're reducing or oxidizing conditions, reducing like H2 or CO gases, or oxidizing gases like H2O and CO2. The second factor that is important is the solubility. So if we already built up quite a lot of H2O in an atmosphere, we will not be able to outgas any more water into the atmosphere. The same is true for sulfur species, for example. whereas CO2, for example, can be outgassed even at very high pressures. This is also long known since 20 years, I would say, from studies from Fabrice Gaillard, for example. One thing that is often not taken into account is that if you actually want to outgas, we first have to think about what is the composition of the melt that can actually then outgas at the surface. And for this, it's a question how to actually volatilize partition between the silicate mantle, like the solid mantle, and the melt that is being produced. So water, I said earlier already, preferentially goes into melt when melt is being produced. For carbon, actually experiments already a long time ago, actually the first experiments by Holloway were before I was even born, so it's known quite some time now, that if you have reducing conditions, then carbon actually does not like to partition into the melt, whereas if you go to more and more oxidizing conditions, at some point more and more carbon can actually partition into the melt. There have been, since these earlier studies 40 years ago, many more studies from different groups that were summarized in this very nice paper from Fabrice Gaillard et al. In 2021, where they actually looked at different factors influencing the carbon partitioning into melt. And you do see here on the y-axis the carbon content in the melt that we could actually potentially have. And you see that there are a few cases where we actually do get large amount of carbon, even for low oxygen fugacities. But there are actually three factors that he actually points out in the paper. So first, yes, if you have an high oxygen fugacity, we would expect carbon to preferentially partition into the melt. That we already knew about. If we have a high pressure, under high pressure conditions, actually also carbon can actually preferentially go into the melt. But high pressure here means high gigapascal pressures. So this is nothing that we would actually experience at the surface or even in near surface melt regions. And if we have a high concentration of hydrogen available, like a hydrated mantle, then we can form basin fluids, and this way we can also get carbon into melts. However, this also means if we do have a low pressure environment, a low oxygen fugacity, and a low hydrogen content, still carbon does actually not like to go into the melt. What we end up with is therefore some kind of a bifurcation system of what kind of outgassing we could expect. On the one hand, for reducing melts, so we first have to consider where can melt actually be produced and rise to the surface? What is about the partitioning of carbon and water into these melts? And then if you have a reducing system, oxidized system, in the reduced system, we would favor outgassing of H2 and only minor amounts of other species, most of all water, but only few fractions of CO or H2S, for example. And in the oxidized case, CO2, H2O, SO2, N2, everything that we see of volcanoes on Earth actually is on the right side of this picture. So what does it mean now? So if we look at the solar system, what kind of atmospheres we actually have there, we see that we have these primordial-like atmospheres from the sun and our gas giants not being too different actually. We have these CO2 bodies in Venus and Mars, but actually the atmospheric pressures we know are quite different. And then we have nitrogen-dominated atmospheres on Earth and also on Titan. On Earth, the oxygen produced by life, but otherwise these are like the main types of atmospheres that we have in the solar system. So is this all that's out there? Can there be other kind of atmospheres, and how common are these different atmospheres, like the CO2-dominated atmospheres, for example? How likely are they actually? And there are, of course, again, different ways of looking at this also from survivability point. So there have been studies looking at, depending on what kind of insulation or installation we actually have, depending on planet mass, which influences erosion, we again see that these main types of atmospheres may indeed be the most likely atmospheres for rocky planets that we could expect. And gas giants, again, for very high mass planets. Just citing one more figure from Gaillard et al. 2021, again showing what different types of atmosphere would expect with different pressures, with different oxygen fugacities. And I want to highlight here also the point that from the observer point of is quite interesting, that we do get quite a different range of mean molecular weights depending on what kind of system we actually have, whereas the low mean molecular weights atmospheres are also more easily eroded, and the heavier atmospheres more stable against erosion, where, for example, a magnetic field is not needed to sheet an atmosphere like we see in the case of Venus, for example. So we can actually look at a specific system and try to predict what kind of atmospheres we would actually expect. And in this case, the TRAPPIST-1 system is actually the ideal system. Thank you so much for finding this system for comparative planetology. It's just amazing. And see what kind of atmospheres we would actually expect there. Again, atmospheres like we see in the solar system, yes or no, or under which conditions we would expect them, or like a Mercury-like case, so no atmosphere surviving at all. And for these, we can actually use combined models from the interior to the atmosphere, also including different things about dynamics that I explained to you beforehand already. This is an example simulation for TRAPPIST-1e, for example. What we do is there we take into account a lot of different interior processes, but also these redox-dependent partitioning of volatiles into the melt, which is quite important for the atmospheres that we get in the end. We also take into account that the chemistry of the interior should actually depend on distance of the star. Though I want to point out again the great talk from Chase 2 days ago in the morning, showing that, of course, a planetary mass also plays a role, which actually here is not taken into account. And otherwise, we have a lot of unknown initial parameters. We don't know how hot these planets start with, how many volatiles they have in the interior, and so on. So what we do there is we actually, for each of these 7 planets in the system, choose 20 completely, well, not completely, randomly chosen parameter sets within ranges of parameters that are most, or let's say an educated guess tells us are the most reasonable ranges. And then we average over these 20 simulations for each planet. And this gives us somehow an idea if there's a trend of atmospheres that we would actually be able to see in the system or not. Again, under this idea of this redox dependence with distance in the system. We then apply these speciation calculations for these gases, depending on solubility, check if an atmosphere is actually forming. And for the atmosphere itself, we take into account that temperatures are changing over time, that we have an exosphere which will be probably hotter than the surface temperature. Here we actually don't calculate self-consistently what the exosphere temperature is. So the height we actually calculate, but for the temperature we assume some kind of a scaling factor, which I will then explain also when I show the results, what this actually means. And then we calculate atmospheric erosion to space, where here we actually use Jeans escape and photodissociation assumptions. We then use a chemical equilibrium code to re-equilibrate the atmosphere after atmospheric losses. And we also take into account condensation of water, which is also quite important for our results. So how do all of these different effects actually matter? Do they actually play a role or not? Well, again, looking at example for TRAPPIST-1e, what we can do is to actually one by one go through these processes that we actually turned on and see what happens if we don't consider the other processes and what actually influences our atmosphere. So if we only look at an oxidized atmosphere, Earth-like volcanic activity, like the very first studies that we did like 10, 15 years ago for rocky exoplanets, then in one test case scenario for TRAPPIST-1e, we would actually say, well, we do get an atmosphere mostly made of water. Well, I'm not talking about realistic atmospheres, right? Just plugging the model in, one process after the other. If we take into account that we have a redox dependence, if it's a more reducing interior, and we add this carbon partitioning factor, what you see is that the CO2 that was previously predicted is disappearing mostly. This is the effect of this redox-dependent carbon partitioning. This is where your CO2 goes. If we then take gas speciation into account, instead of water, we have mostly hydrogen and water outgassing under these reducing conditions. If we then add the effect of solubility, which has a strong effect on water, but not at hydrogen, our atmosphere would become more and more hydrogen dominated. Again, I'm not talking about realistic atmospheres, just turning on one factor after the other. If we take into account condensation, all of the water would be gone because depending on the temperatures that we assume here for TRAPPIST-1e, habitable conditions, not much water can actually stay as vapor in the atmosphere. Most of it would actually condense at the surface. Adding then chemical equilibrium will actually also change the equilibration between the outgas nitrogen, and the nitrogen would become ammonia, and we would still have hydrogen. So completely different than what we saw in the beginning. Weak genes escape means almost no escape considered here. But if we take strong genes escape into account, most of the hydrogen would be lost. The ammonia would actually split up again in nitrogen and hydrogen being lost again. So if an atmosphere would actually survive at all in these scenarios, it would actually be stripped of these reducing components, and we would actually be left over with a nitrogen-dominated atmosphere, and in this scenario, a little bit of CO2. 1.6 bar in this case. But again, each simulation has different values, right? This is why we're taking these random simulation parameters. So this is only one example. We can, of course, also compare how would this actually change for when we assume a very oxidized state. So I said in the beginning, we assume here in this TRAPPIST-1 system, like an increase of redox state with distance from the star. So while for TRAPPIST-1e, we would still assume moderately reducing conditions. In our scenario, the outermost planet, which probably had a lot of water to react with, would have become very oxidized, and therefore we assume here a rather high oxidation state, iron rutile +4. So what you can see here first in this top panel is a comparison of an atmosphere that we would get if we only consider volcanic outgassing without taking any of the other processes into account. And we would end up with something like a 20-25 bar atmosphere in this case, but with turning on all our different processes. In the end, we only end up with like a 1-2 bar atmosphere. For our oxidized case, so the outermost planet, this is not the case. There, really, our Earth-like outgassing ratios would give us pretty much the same that our more advanced model would actually give us. This also is related to very different species, or the major species are shown here that would actually be volcanically outgassed and accumulate over time in the atmosphere. So here is a mass of atmosphere in kilograms shown. So here for the 1H system, you would immediately build up a strong CO2 atmosphere. So this could be like an exovenus-like system, even under these colder temperatures that we have there. Whereas on the left case for the TRAPPIST-1e system, we would form an ocean quite quickly, and only at the end, the ocean would actually start to evaporate back into the atmosphere with hydrogen being eroded away. For most of the time for the TRAPPIST-1e system, we would expect an atmosphere dominated with ammonia and then nitrogen taking over. And only at the end, when we still have a lot of water evaporating, hydrogen being lost, a lot of oxygen being built up. Very similar to these early studies that looked at magma ocean, water steam atmospheres, building up a lot of O2, but these studies didn't consider other species like carbon and nitrogen. So we can then compare now the different scenarios of weak to strong or very strong escape along this TRAPPIST-1 system. And again, if we take into account extremely weak, extremely unrealistic escape, so we don't believe that this is a scenario, we just want to show what is, again, the effect of this redox state over the system that we assume from reducing, so somewhat Mercury-like at the innermost planet and more Earth-like oxidation state at the outermost planet. And again, the innermost planet would be mostly, if we have almost no escape, mostly dominated by hydrogen, and the Venus-like or more Venus-like CO2-dominated atmospheres we would only expect further out in the system. The only exception being TRAPPIST-1d, because it's so small, almost no gravity, it anyway cannot keep a hydrogen atmosphere or water atmosphere. However, these are more unrealistic scenarios because there's been also other studies. So there's Gwendal also has a poster here showing how the due to the different way how the luminosity of the TRAPPIST-1 system compared to the sun evolves over wavelengths. The XUV luminosity is much, much higher in the habitable zone around TRAPPIST-1 than it's for the sun. And so you can actually have much higher EUV fluxes, and then N2 and CO2 dominant atmospheres may also start to be eroded. So what we did here now is to take this idea that exobase temperatures can be much higher into account, and then again apply the same simulations, again 20 random simulations, and I only show the average result of these 20 simulations over 7 billion years. And what we see here for a stronger escape scenario, that actually these innermost planets, they all lost the hydrogen and water, and what they actually build up are nitrogen, oxygen atmospheres. So even here in the habitable zone, the atmospheres that we would predict, if they exist at all, at stronger erosion, we would have no atmosphere. But for the more or less realistic scenarios of atmospheric escape, the atmosphere would all be nitrogen, oxygen atmospheres, completely independent of life, has nothing to do with life production. This, of course, in the scenario of biosignatures of finding life is quite problematic, but maybe very interesting test scenarios, especially for these hot, rocky exoplanets around M dwarfs in general, because these are atmospheres that may fit to what we've seen so far. There may be no atmospheres, or these very thin nitrogen atmospheres with a little bit of oxygen, maybe a little bit of CO2, but definitely not these CO2-dominated atmospheres. So this answers the question, where is the CO2? And I leave you with the conclusions.
Thank you. Are there questions? Are there questions online by any chance? Early birds? No? I have the microphones. Do you have a microphone over there? Okay, let's start there.
Bennett Skinner, McMaster University. Throughout your talk, you've shown a lot of the average results of various simulations. Could you comment a little bit on what the spread, what the distribution looks like?
Yeah, so exactly for the planets where we have stronger escape scenarios, very often we only get nitrogen atmospheres, or we get the nitrogen-oxygen atmospheres in different proportions. But actually here in these cases, we don't see the carbon enrichment because of this carbon partitioning effect. And so we always end up with more or less the same atmospheres or no atmospheres if the escape is even higher than that. If you go to these atmospheres, so if you go to higher and higher redox states, then we see quite some variability, sometimes even a methane atmosphere, or sometimes a CO2 atmosphere, sometimes a CO atmosphere. So here in this range, you also see it's much more colorful. It's not from one simulation, but there are different simulations picking up different kind of gases. But here for these innermost cases, so if you have a reducing planet close in around an M dwarf, there is, I would say, from this simulation, no chance but to get a nitrogen atmosphere or even nitrogen-oxygen atmosphere.
Okay, other questions? Yeah, you.
Hi, Will Meisner from Carnegie Science. Really interesting talk. I was wondering, I think maybe you were sort of getting at this, but I was wondering kind of specifically about this plot again. For the outer planets, it seems like when you have stronger atmospheric escape, you actually end up with much thicker atmospheres.
Yeah.
Can you take me through kind of what happened there?
Exactly. So what we take into account here is condensation of water from the atmosphere building up oceans as a surface. So actually, if you, for this upper row, if you would actually put all of this ocean into the atmospheres, they would have higher atmospheric pressures than in the lower row. What happens if you have more and more hydrogen escape, you have more and more leftover oxygen building up in the atmosphere. And since then you have no water vapor, the ocean starts to evaporate back. So this is why we actually get these lower, higher pressures, but very well observed.
Yes.
Took us a while to figure this out, where it comes from.
Thank you. Yeah.
Xue Chongyang, ETH. So I think you show one video of your 2D simulation, but at the very top there is a water depleted layer, and I'm curious, what is it?
Yeah, I mean, here this is for general melt depletion. But the thing is that we start actually with stagnant lid in the beginning, which has in a way, so it's a water enriched layer, not a water depleted layer. So normally it should be, so at least here when we look at the depletion, it should be like there is no melt in the lithosphere itself because it formed very early and then remains cold and is not being molten anymore. For the water, let me actually quickly check. It may be the initial water profile that we actually start with. So this would be more or less the water. So in plate tectonics, we actually erode all of the water. We have the dry surface because we don't really build up the lithosphere. But here we have a thin water-rich layer in the top. In a way, we have a hydrated crust, a hydrated lithosphere that we just don't touch during our stagnant simulations.
Okay, thank you.
Thank you. You and then you. Yeah. No, you first.
All right, thank you. Gerge Frischuni of Edinburgh. Thank you for the great talk. My question would be for the tropism models. The running time or the simulation time was quite a couple of billion years, if I remember well. How does that tie into what we observe? I don't know the age of the TRAPPIST system, or like would we see the planets at their age, or is this like a
So
converging?
for the TRAPPIST-1 system, we took here the suggested average age was about 7.6 billion years right now. There is some insecurity. It could be a little bit younger, it could be a little bit older. And there it's exactly where the interplay between erosion and outgassing becomes so interesting. I go back to this slide. So if you would actually look a little bit earlier, of course, it depends on the strength of erosion also. We actually do change the atmospheres over time. So depending on when you look at the atmosphere, you may see different compositions. Unless you are in this more Earth-like outgassing with the CO2-dominant atmospheres, nothing changes.
Thank you.
Hi, I'm wondering how or if the one-to-one tidal locking affects these models.
So tidal locking is not included. What is included here is if you have the eccentricity of the system of tidal heating. So this is included. The tidal locking is in the interior. There have been models from Tobias Meyer, for example, showing how the dynamics can be a little bit different and also volcanic outgassing. So there are some effects. Also, Philipp Baumeister has been also working on this. So we do see different effects for outgassing rates, depletion for the night side and for the day side. But here I think it's more about atmosphere circulation, where tidally locking becomes important, or the question of a magnetic field then. So this we have not taken into account here.
Thank you. Martin Schlecker, European Southern Observatory. Thank you for the great review talk. You mentioned that it's hard to predict, or we cannot predict if a planet is stagnant lid or a plate tectonic. So does that mean there are no observables for a specific planet if it is likely a stagnant lid planet or plate tectonics? And if not, is there at least hope for some population level signature that in a larger sample?
Well, it now becomes very speculative and more philosophical answer, maybe. But the thing is, if we do our simulation for stagnant planets and we say that we wouldn't expect active volcanism, strong volcanism for a 6 or 8 Earth mass planet, and then we see recent SO2 outgassing or something like this, one could argue that maybe this means there is plate tectonics. We could have a look at if there's a magnetic field or not, which is actually here we stopped at 2 Earth masses, but if you go to very massive planets, at stagnant planets, again, we would not expect a magnetic field. If we would indirectly observe one, we could argue more, maybe some kind of mobilization happening there. But I think it's only indirect proof that we can get. Interpretation of the observations, but no 100% proof of plate tectonics.
No smoking gun.
At least no one yet came up with an idea that I heard which could reveal 100% proof of plate tectonics.
Thank you.
Okay, then we go to the last question, and Julia, you can sit up.
Hi, Sophia Vaughan, Max Planck Institute of Astronomy. I was just wondering, so the pie charts you showed had quite a lot of oxygen in them. Would atmospheric combustion potentially be a problem? And is this included in the model? As in,
So can you say that again? What would be problem?
Would it be a problem to have so much oxygen because it could combust?
So there have been studies for Earth that if you go to higher ratios than about 30% of molecular fraction of oxygen in the atmosphere, our forest would start to burn up and would reduce the oxygen again. So if you have something that can burn in a way, like our forest can burn, there may be an upper limit. So the 30% idea is very strict limit to the past, what we see on Earth. So I would say 50% may still be possible. And if you don't have life at the surface, if you don't have anything else than rocks at the surface, these papers all talk about combustion on an Earth-like surface and not on a Mars-like surface. So as far as I understand, then there's no limitation even for higher oxygen, but a pure oxygen atmosphere, I think we would not expect.
Okay, thank you.
Okay, thank you very much. Then with this, we thank Lena. And then we move on to the next speaker, Giulia Rocchetti from ESA. And I think you're ready. Yeah.
Hi everyone, can you hear me well? So I'm Giulia Rocchetti. Thanks for the organizer for the opportunity to present my work. Today I will present how we have been using Earth-shine observations to try to find a way to characterize rocky exoplanets. So let me start by telling you what is Earth-shine, because it might be something you never heard about. So Earth-shine, in my opinion, is a nice way to try to actually have a replica on how we can observe the Earth in reflected light. And to do that, what we actually do is to take the sunlight, which get reflected or scattered by the atmosphere or the surface of the Earth. Then these photons can be reflected on the darker portion of the visible moon and get back on our ground-based telescope on Earth. So this is, of course, technically very challenging and observationally as well. But the nice thing is that we completely lose the spatial information of where these photons get scattered or reflected on the surface of our planet when we go on the moon. Thus, we get a signal which resembles the way we observe a planet as a single pixel. So essentially as a spatially unresolved exoplanet. So what we're actually doing is basically using the moon as a diffuse mirror. As of course, we can all argue the moon is absolutely not a good mirror. So the challenge of this observation is, of course, to correct for the lunar reflection. And at the same time, as you can see here, the other big challenge comes from the fact that we have our reflected light component, which is actually is what we actually want to measure. But later on, we also have a transmission through the Earth atmosphere, which is going to imprint on top of our observations against some telluric lines. So to get rid of this second component about transmission, a smart way of doing that is actually performing these observations using polarization. And the reason is that we basically do not going to change the polarization state of our observations when we when we do the transmission. So observing with spectropolarimetry, so getting the polarization information as a function of wavelength, can really help us like discriminate between the actual reflected light component, which is what we want to measure from the transmission. So in general, what is cool about the dispersion observation is that they've been used since like way back in time, and they can really give us these simultaneous hemispheric albedo, or let's say reflected light observations of the Earth. You can even get from satellite observations like in this simultaneous way, which is very cool and very powerful. And at the same time, they can really represent a benchmark on how we can study the Earth as an exoplanet in reflected light or polarized light, as we can observe this system at different phase angle as the Sun, Earth, Moon system is gonna change like by night. All right, so we have a large catalog of these ocean observations we collected over more than a decade, starting more or less in 2012. And this has been done with the FORCE-2 spectropolarimeter at the VLT. And here I'm just representing a small subsample of some simulations of the exact date and time of these observations. So as you can see here, we can cover like this big range of phase angles from more or less this 33 degrees of phase angle up to like a small like fraction of the illuminated side of the planet up to like 135, 140 degrees of phase angle. And of course, we can cover a lot of variability. So we can have like some scenarios with illuminated side of the planet over more or less kind of an ocean planet. We have almost no land in the illuminated part. We have other parts with continents. We have, of course, evolving weather patterns, cloud scenarios, and so on. And what you want to do with this, of course, is try out your model and go in detailed modeling of this and see, okay, what we need to inject and how complex needs to be our model to actually replicate this catalog of Earthshine observations. So what we do is to use a 3D Monte Carlo radiated transfer code. I'm using MYSTIC, which is actually developed to do Earth remote sensing studies. And with MYSTIC, we can really input 3D atmospheres with realistic 3D cloud structures, 2D surfaces, and so on. However, the big challenge I faced at the beginning of my PhD when I started to like deal with these simulations for matching these observations. Sorry. All right. So is that if we look at these observations and how like previous attempts in modeling them were like actually we're not really agreeing in the matching of these observations. We can see two different examples. The first one is actually the observations are this gray line up here, and you can see different models attempts. And in particular for this epoch, you can see that both the level of the continuum in polarization, so this is degree of linear polarization as a function of wavelength, would not be really matched between the simulation and the observations. At the same time, also the spectral slope, the absorption lines. This other case is even more extreme, so you should look at the corrected Earthshine in red, which is what you would like to match with your model, and the DAP and V-star model are down here, so you can see really there is absolute no match with the observation. This is, of course, very concerning. Is it true that polarization, of course, is more complex in modeling, but at the same time, it should be the Earth, and we have a lot of input data we can inject, so it's concerning. We cannot really get at all a match with the observations. So what I've been investigating in terms of, okay, what can we try to do better, what we're not getting right in our model is, first of all, how we represent surface albedo. So what I've been developing is a data set to really treat the wavelength dependence evolution of the surface albedo of our planet. So I just took basically a large data set of surface albedo observations from satellites, in particular from MODIS in the visible and near infrared. However, they only give you some few bands of observations from like 7 bands, and I've been interpolating them in the wavelength space using a very large catalog of laboratory and in situ measured spectra of the reflectivity of soils, vegetated surfaces, and so on. And what you can see here is like one example for one particular day. So we can see how the albedo of the Earth changes as a function of wavelength. We can see that here is gonna get very bright when the vegetation red edge peaks start to kick in, and moving in the near infrared, the ice caps are gonna get like lower and lower in reflectivity, or near in the near infrared again, where out of the vegetation red edge main peaked. And as we like keep going in the near infrared, we see how relevant the deserts are gonna be shown. So this is really a way to try to better represent surface albedo. And we can see which is the impact of actually applying this data set into our spectra. So going again in the disintegrated properties of the planet. And we can look at this both in reflected and polarized light. So here you see 3 different examples for 3 different phase angles. This is reflectivity and this is polarization. And here you can see the difference between a constant albedo and these wavelength-dependent albedo maps. So you see that they matter mostly for high small phase angles, configuration, and reflected light. They're important also in polarization, and they even change the spectral slope of our of our simulations, which is one of the goals we were also trying to achieve and to try to explain where this mismatch with the observations was coming from. But the key component was absolutely not surface albedo. The key component really came from how we treat clouds. We all know clouds are complicated, and like this is a satellite observations from the NASA's Discover satellite of one random day of the Earth. And what was very concerning for me was that when I first tried to look at such a replica from my simulations of this configuration of the Earth with our clouds, this is what I got. Here, of course, you can argue, okay, which cloud data are you using, or you are injecting them into your model, and this is really a very well standardized cloud dataset coming from ERA 5, which is a reanalysis model, meaning this is a weather forecast model, which is later on improved with injected satellite observations. And to actually get something that much better resembles the satellite benchmark over here, what I need to do is to develop a cloud generator approach. What is a cloud generator? So I made a simple sketch to try to explain the key idea. We basically want to still keep the microphysics of these validated satellite observations, but we just want to divide them into subgrids. So we want to run our 3D radiative transfer scheme within this patchiness instead of like in this mirrored out cloud configuration, but still conserving like the global cloud properties and their microphysical properties. And doing that, we can look at the impact of having this 3D cloud generator again on our spectra. So you can see here the reflected and polarized light at different phase angles. And here you can see also the impact on the simulated images of the horizontal resolution of the clouds. And you see again a huge effect over here. So you see how you decrease the reflectivity more or less independently on the phase angle. When you look at the reflected light spectra, we are speaking of a bias of 20–30%, while in polarization, you see that there is definitely also a phase angle effect, and you see how much you increase your linear polarization component when you go to smaller subgrid cloud variability simulations, and you also really account for the cloud heterogeneity. So this is really a key result, which allowed us to then go back to our initial sample and plotting 4 different spectra, randomly selected from the catalog, and now you can see how much better we can match between the observations and the simulations, considering this improvement both in the surface albedo and the clouds modeling for our planet. This is just to say that also in reflected light, this matters a lot, meaning that if we consider this improved reflected light simulations, and if we consider, for example, with the Andes golden sample from the pave paper, we see basically half the reflected light contrast that was calculated for this planet. So this is really important also for predicting future instruments and our what we should expect for the characterization of rocky planets. So I'll leave here my conclusions. So saying that Earthshine is really a nice benchmark to study the Earth as an exoplanet reflected light and to prepare for future generation of missions. And at the same time, really how we treat clouds and surface albedo, it's very important for the results we're getting, and even for the Earth, this should be better validated. Thank you.
So we have time for at least one question. Yeah, all the way in the back.
Thank you. Evelyn McDonald, University of Vienna. I'm wondering if you could say a bit more about how you're going to do this for exoplanets, in particular with regard to the clouds, because if I understand correctly, your clouds your cloud model is largely based on Earth data. So yeah, how does one do this for other planets?
Yeah, thanks for the question. It's so the key idea is that I think even from predicted clouds from GCM outputs, so if we take a particular planet, what would try to do and try to imagine to do is to then also try to get in like smaller and smaller grids, and how we represent then the clouds before running like our radiate transfer, meaning that we should try to develop ways and introduce this like subgrid cloud variability, because what I really found is that really the horizontal grid resolution matters a lot and give us these very unbiased like top of atmosphere fluxes and in general disintegrated spectra. So I still believe that, of course, depending on the planets and depending on like the overall cloud properties, this can matter less or more or less, but I would still like try to divide the clouds from the GCM into subgrids and run the results with that.
Okay, thank you very much. We have no time anymore for further questions, so please approach her in the coffee break. And let's thank her again. And the next speaker is Janina Hansen from ETH.
Sorry. Yeah, thank you. That was a rough test. I'm sorry. So I guess you hear me okay? Should I get it closer? I'm not doing it again, I promise. Should I? Yeah, looks good. Thank you. All right, so good morning, everyone. I'm Janina. I'm a PhD student at ETH Zurich, and I will talk about chemical disequilibrium biosignatures, or in other words, we will reflect on our work-life balance together in the next 10 minutes. Here's our step-by-step guide of our quick session this Friday morning. First of all, I get into, in general, how modern life and the concept of a work-life balance can fit together in the first place. And then we take a little bit of a breather and talk about the role of molecular oxygen. And then best for last, we'll bring some life to the work-life balance. So let's get us started. In a modern Earth atmosphere, we do have both methane and molecular oxygen present. This is something that might not be surprising to you, but it could actually surprise you, because you would not expect to have any methane left in such an oxidized atmosphere as our modern Earth atmosphere in the first place. And this is because we have processes like this at play. Methane oxidation, where O2 and methane form to react H2O and CO2. And this process would actually relatively quickly deplete all of the methane that we have in our atmosphere. However, we do still see both methane and molecular oxygen present. And this is because we have biological processes at play. We have oxygenic photosynthesis and methanogenesis fueling both oxygen and methane back into our atmosphere. So the fact that we have these two long-term incompatible gases coexisting represents a chemical disequilibrium. A chemical disequilibrium that is sustained, fueled by life, by biological processes on our Earth. And the disequilibrium is something that we can quantify. Here's just a simplified sketch. This is a simple box of gas that is well mixed, constant temperature, constant pressures. We do have some oxygen in there, some methane, some nitrogen. This is supposed to resemble a simplified modern Earth-like atmosphere of how we might observe it. Now, in order to estimate how much the atmosphere is out of equilibrium, we need to know how our equilibrium state looks like. And here, thermodynamic theory helps us out, which tells us that the combination of gases or species in the atmosphere that minimizes the Gibbs free energy equals the equilibrium state. So then in the end, we can take a simple difference between the Gibbs free energy of our initial out of equilibrium state and our equilibrium state, which we then also commonly denote as the available Gibbs free energy, which is here our metric to quantify the chemical disequilibrium in the atmosphere. Now, you can also think of it as the maximum amount of work that is extractable from the system. So a quick analogy for you. So you can think of life naturally as producing some leftover work. And it's lying on your desk, it's piling up. There's no one else around to pick that work up for you, but it's getting later and later, and it's Friday evening, and you want to go into the weekend. So you just go into the weekend, you feel fine about that leftover work on your desk. That way you have produced some disequilibrium, but on the other side, you're also actually on quite a good way to achieve your own work-life balance. Might be something to think about later tonight for some of you. So this is why the chemical disequilibrium is interesting for us to look into, because in our modern Earth atmosphere, we know that it's biologically driven, so it might be interesting to look for this on other, ideally terrestrial exoplanets as well. I do want to go into one specific detail here for a few minutes, and that is the specific role of molecular oxygen in this. So I've showed you this simplified sketch here of the atmosphere out of equilibrium before. This is nothing new. The new question that I want to raise is, what role does this additional oxygen molecule play here in an atmosphere for the disequilibrium? Or maybe a more drastic example, what about that bottom scenario here, where we have much more molecular oxygen in the atmospheric mix? How does the disequilibrium change between scenario 1 and scenario 2? And having another look maybe at that reaction here, you might conclude that actually the degree of disequilibrium should be the same, because in both of these atmospheric states, we have oxygen abundances that are larger than twice the methane abundances. So we're limited here by the reactant methane, so that oxygen molecule has no other reactant partner to react within that context of that specific reaction driving here the disequilibrium. We can also try to quantify this. This plot was done using AtModeler, which Dan Bowers talked about much more, and it does many other great things. The only simple thing I did with it here was looking at modern Earth-like atmospheres and then vary the amount of oxygen over many orders of magnitude and the amount of methane in those atmospheres. The color bar here on the right tells us how much disequilibrium is present in those atmospheres. So the lighter green we go, the higher the degree of disequilibrium. And I want to walk us through one specific example, that is the one of modern Earth methane abundance around 10 to the minus 6. So if we move along this arrow and we increase the oxygen abundance in the atmosphere, we would also get to these lighter greenish areas. So we have an increase of disequilibrium until we reach exactly that sweet spot where our oxygen abundance surpasses our methane abundance. And here adding more molecular oxygen to the mix does not further increase the degree of disequilibrium. So if you could see this, we're now moving along these contours instead of crossing these contours. So staying roughly at a constant disequilibrium level. Now, the reason why I spent relatively much time in this 10-minute talk of trying to drive this home, because from an observational perspective, this strongly simplifies the kind of constraints that we need to put on the degree of molecular oxygen in the atmosphere on this abundance. Because now if we have a proxy or a signature that tells us that we are in this insensitive high oxygen regime, this is then already sufficient for us in order to derive correctly the degree of disequilibrium, because we know we're then in this insensitive regime. And I say this because we can use now ozone as a sufficient proxy to tell us whether we are in these very low trace oxygen amounts or in these high oxygenated atmospheres, which is interesting if we come from a mid-infrared observational perspective. All right, we've talked a bit about work. Let's talk a little bit more about life. Life stands for the Large Interferometer for Exoplanets. I don't want to go into many nitty-gritty technical details, but I do want to get a few points home. So similar to HWO, life is a direct imaging mission. And this is not a coincidence. There's specific reasons why our future lies apparently in the direct imaging detection and atmospheric characterization. And this is because for every planetary system that's transiting, we have more than 100 systems that are non-transiting. And we do want to be able for these next generation missions to also have access to these kinds of populations. Secondly, life is operating in the mid-infrared. This has a few key advantages. In the optical, we need to hit a contrast requirement of 10 to the minus 10 in order to resolve and detect an Earth-like planet around a Sun-like star. In the mid-infrared, it reduces to 10 to the minus 6, so 4 orders of magnitude less stringent contrast requirement. Second advantage for mid-infrared is that we're actually probing the thermal emission of the planets themselves, which means we actually can probe deeper into the atmospheric layers. For a modern Earth-like atmosphere, taking the full cloud coverage and everything into account, the atmosphere becomes optically thick almost right up onto the surface. So we get this crucial context information of surface pressures and surface temperatures, which also in the context of these future interpretations of these spectra and trying to identify biosignatures, giving us this crucial context is important to make sufficient and more based claims about what we're actually seeing. And then the last point, so why do we talk about this if these are future missions, next generation? Because someone needs to work on making these missions fly in 15 to 20 years. And this is what we're currently doing, trying to provide the next generation kind of data to find some next generation kind of answers for questions we've asked ourselves for many, many generations. Okay, that was my quick pitch to life. If you have more technical questions, let me know later. I want to show you some first preliminary results in this chemical disequilibrium kind of project. How well could we constrain those in modern Earth-like atmospheres with life-like observations? First step in our pipeline, we need some noisy mid-infrared spectra. Thank you. For this, we could simulate atmospheric compositions and so on. What we've done here is take actual empirical satellite data from the Earth. So kind of the most complex data set that we could kind of look for modern Earth-like scenario in terms of atmospheres. We infer the pressure temperature profiles, the abundance profiles, and then we can use this to infer the thermal mid-infrared spectrum, which we then scale to 10 parsec in order to mimic an exoplanet-like observation. Now, the envelopes you see here on top of these spectra are the noise estimates that we can derive with our in-house noise simulator, which is called LiveSim. Here it includes the major astrophysical noise sources. Currently, we've also updated this to include instrumentational noise, but this is not what I show you currently on these slides. Next step, we do some atmospheric retrievals on our noisy spectra. Here I just show the results for ozone and methane, because in the context of that modern Earth-like disequilibrium, these seem to be the parameters that we are hunting for. The different colors here indicate different spectral qualities. So if we go from resolution 50 to 100 and signal to noise 10 to 20. Our ozone constraint looks quite good. We're quite constrained level here of the abundances of ozone in a modern Earth-like atmosphere. And this actually tells us that we're in this high oxygen regime, which is what I explained earlier. Good for us when we're trying to look for mid-infrared observations here and using ozone as a proxy for molecular oxygen. And then for the methane, I do want to point your focus here on the dark blue line, which is the lowest spectrum quality, resolution 50, signal to noise 10. And here we're maybe getting an upper limit, but not doing as good of a job as in the other spectrum quality cases. And this then also translates to the thermodynamic models that we input our retrieval results into. And here we can see also for this dark blue scenario, we're underestimating here a little bit the available Gibbs free energy, so a metric of disequilibrium, whereas in the other cases, we're already doing quite a good job. However, this is still work in progress, so there are a few more analysis steps on the way before we published it. Before I leave you with the summary, I do want to make a quick pitch about the previous project that I've worked on, where we looked at population of atmospheric trends. So here we tried to infer atmospheric CO2 abundances as a potential link to surface water and maybe even biotic activity. So if you're interested, you can check that out. That's already published. For the rest, you need to wait a little bit longer until you see that somewhere. But I leave us here with the summary slide. Thanks for listening.
Time for at least one question. Oh, there's a question online. Great.
Hello, this is a question from an anonymous attendee. If we do detect chemical disequilibrium on exoplanets, how do you envision determining whether it is because of life or because of something else? For example, mixing or lightning?
Yeah, so this is a good question. So in the end, again, driving just the degree of chemical disequilibrium cannot be sufficient in giving us the information whether this is biotic or abiotic. What we would need to do is look at the specific species and look at the processes that could drive large abundances back into the atmosphere. So here again, we need some other context. It cannot be just the degree of disequilibrium in itself. However, what I've said previously is that at the mid-infrared, we're probing deep up onto the surface, right? So no, we're not probing the upper atmospheric layers, we're actually probing deep into the surface. So we get like a closer look at what's actually close to being outgassed at the surface as well. So we might not be as sensitive to then these changes of photochemistry and so on, as where maybe other, wavelength ranges might be limited by. Yeah.
We have time for a really quick question. Okay, no further questions. Then let's thank the speaker again. And then we move on to the next speaker, Martin Scheckler. Working? Yeah.
Great to see everyone throughout the week. My name is Martin Schlecker. I'm an ESO fellow in Garching. And we've already heard in these exciting previous talks about biosignatures and how hard it will be to detect even a single convincing one. But today I would like to invite you to explore what we could do with a population of biosignatures and non-detections as well, but also how we can take a statistical approach to questions of habitability. So if we look back to the early times of exoplanet science, we see that the progress was initially made mostly by individual discoveries, right? The first exoplanet, the first hot Jupiter, first super Earth, and you get the Nobel Prize and you're happy. But as the sample grew, the major breakthroughs increasingly came from statistical trends. We have seen that plot before, the radius valley or occurrence rates as a function of spectral type. And so this shift essentially created the subfield of exoplanet demographics. And I believe that we're going through a similar development also in studying planetary habitability, where more and more the source of highest science return comes from not so much system science. It shifts to a comparative planetology approach where we're not deeply characterizing individual planets, planetary systems. We're doing that as well, and it's super important, but more and more we get information from statistical or distributions of key observables. So what do I mean by that? Just one famous example is, of course, a simple concept, the habitable zone. And there are a number of statistical predictions. I will just show two examples. The first one is about a significant radius increase due to a runaway greenhouse transition. The idea here is that interior to this transition, we have steam atmospheres that blow up planetary radii such that a radius discontinuity emerges. And the second example looks at a different observable. Here the prediction is that within the habitable zone, the planetary albedos are statistically lower. Why is that? Interior, we again are more likely to have a thick runaway greenhouse atmosphere, which is highly reflective, whereas outside of the habitable zone, we're more likely to be globally glaciated, which of course, again, is very reflective. But how can we test predictions like these? Well, one approach that has been used a lot recently is one of statistical hypothesis testing. And for this, we developed our framework BioVerse. BioVerse connects theoretical predictions with survey design and statistical inference. And it allows you, if you have a concept for an exoplanet mission or survey, to instead of just calculating a planet yield, really answering the question, what are the scientific hypotheses that my mission will be able to test? Or how do I have to do the survey in order to test my hypothesis? It's open source, and we have extensive documentation and little tutorial notebooks. It's fun to play with them, and it's also being used in an increasing number of projects. So if you're interested, feel free to play with it. It's fun. But coming back to this initial idea of a runaway greenhouse transition, we recently applied BioVerse to simulate the transit mission of Plato. So the transit survey and assess its ability of probing this predicted habitable zone inner edge discontinuity. We found that Plato will actually likely be able to test this hypothesis, but more importantly, the diagnostic power of this test depends a lot on the availability of radial velocity follow-up observations, because we need the densities, but also on a sufficient sample of planets orbiting M-dwarfs. And meanwhile, there have been several other exciting projects using our framework. And I think that what this really highlights is that there is a shift to a comparative planetology approach also in astrobiology. But then recently we looked a bit into the future, a future where we actually are able to sense biosignatures on rocky exoplanets to test what high-level hypotheses for the origins of life we could test with future exoplanet surveys. In other words, can we use astronomical methods to learn something about how life emerged on Earth? And one such hypothesis is, in the so-called cyanosulfidic scenario, that prebiotic chemistry needs sufficient UV radiation. And these are just some representative photochemical reactions for building the macromolecular building blocks of life. But the key point here is that we need these high energy photons to get the reactions going. And so the hypothesis that we can derive from this is that only planets with near UV fluxes that exceed a certain threshold at some point in their history can show atmospheric signatures of life. So to test this hypothesis, we simulated a population of rocky exoplanets based on Kepler demographics with a near UV flux evolution that is based on empirical estimates from GALEX. And then we also assumed a random abiogenesis rate, random across orders of magnitude. We really don't know how common life is. But then our main requirements for a planet to develop life and biosignatures is that it is in the habitable zone, that it has, at some point in its history, received a flux of UV above a certain threshold. We don't know what that threshold exactly is. And that both of these conditions are fulfilled for a minimum duration. This is our assumed abiogenesis timescale. And here 1 megayear was the default, but in the paper, we explore that parameter as well. And then this gets us a distribution of maximum received UV fluxes, where for FGK stars it looks like this, and the biosignatures can then emerge only above a certain flux threshold. So let's try to find out if a realistic transit survey targeting planets in the solar neighborhood could actually conduct a statistical test for or against this hypothesis. So that's what we did here. And we find that we can actually obtain strong evidence from sample sizes of around 100 characterized planets. I don't know if this is good news, but it gets worse. Of course, the abiogenesis rate that is underlying this can also not be too low. And this is, of course, a parameter that we're completely agnostic of. So here we mapped out where we have statistical power. What that means is that the survey is likely to end up with a statistically significant test. And a key finding that we learned from this exercise is that samples of planets orbiting M dwarfs, again, overall yield higher chances of conducting a conclusive test. But not only that, we also showed that under this hypothesis, these planets are more likely to develop biosignatures in the first place because for M dwarf planets, the time where they receive sufficient UV flux and occupy the habitable zone is larger. So maybe it's time for a reality check here. What does this mean for our near future missions? And going forward, I see two strengths of this approach and one challenge. First, I hope that this example showed that in principle, we can employ our astronomical tools to learn something about how life emerged on Earth and elsewhere. By mapping out the parameter space that allows abiogenesis, we can also better assess how plausible a candidate biosignature actually is. But the challenge is, of course, that for all these upcoming missions like the ELT, HWO, and LIFE, the expected sample sizes seem to be just a bit too low for this hypothesis testing part. So that's a major bottleneck for the statistical tests. But to end on a positive note, just like the foundations of exoplanet demographics were, of course, laid before we had statistical samples, I still think now is the time to get started with hypothesis-driven astrobiology as well. Thank you.
Any questions? Okay, no questions at all. Look, there's a question in the back. And then if we have time, a question in the front. Who raised their head in the back? Yeah, excellent.
That was really interesting. Thank you. Madeline Broom, UC Santa Cruz. I mean, we all know the habitable zone is a super complex zone. How are you defining it here? Is it just semi-major axis?
No, it's an irradiation space. It's the classical Koparapu habitable zone that we're using here. So we try to keep that part simple because, the expected data will also not be complex enough to use more complex models. So yeah, here this is just a simple approach.
Makes sense. Thanks.
Okay, we have time for one more question here in front.
Thank you. That was really interesting, Tad Kamasic, Oxford. So my question is about this idea of looking for a jump in radius at the habitable zone inner edge to see the runaway greenhouse and the resulting inflation. My question is, did you include the potential scatter due to bulk composition and, as Lena just talked about, outgassing that could change the amount of CO2 in the atmosphere and then the resulting scale height and the resulting radius inflation?
We did not. What we used were mass radius, available mass radius relations. And then for within the runaway greenhouse zone, we used the model predictions from steam atmospheres. But then because we knew that not all of these planets in this zone will have water, will have an atmosphere, will be in the runaway greenhouse state when we observe them, we just introduced a dilution factor that gave only a fraction of these planets these increased radii. But they come so the transit radius, they come from these model predictions. Yeah.
Thank you.
The Turbay et al. Models, if you're interested.
Okay, thank you. Let's thank the speaker again. And then we move on to the last talk before the coffee, and that will be given by Mark Braam from the University of Bern.
Yeah? Okay, that's better. Cool. Thank you. All right. So I'm Mark from the Center for Space and Habitability in Bern, and it's my pleasure to talk to you about some works about prebiotic feedstocks and in combination with hydrocarbon complexity in exoplanet atmospheres. So it's a nice timing for this talk because after the review talk by Lena and after the talk by Martin just now as well, I don't have to say that if we go back in time, Earth was a very different place. And if we go back to the timing of the origin of life, we think there was a somewhat reducing environment in which some prebiotic chemistry happened to go all the way to small molecules that you can see in the outer ring of this nice figure here created by Ollie Shortall, to something resembling life all the way in the middle. Now, there's a lot of steps involved here, obviously, some steps that we have some understanding of, some steps that we don't really understand. But I would argue that any of this chemistry fundamentally depends on the creation of these small molecules or feedstock molecules in the outer ring here. Examples include nitriles such as hydrogen cyanide, aldehydes, formaldehyde, and hydrocarbons such as the simple acetylene over here. Now, of course, the production of these species, again, depends on environmental conditions, be that stellar radiation, lightning, temperature, and so on and so forth. And therefore, as Martin also said, exoplanets offer nice test beds for abiogenesis theories. Now, I would say, to understand this completely, what we need in the end is 3D photochemistry simulations. And some people that know me longer also know why I say that. But what we need for this is an accurate but small enough chemical network that can actually describe this chemistry surrounding feedstock molecules in detail. So we use the Vulkan photochemistry code, which solves the continuity equation in a vertical column of the atmosphere, basically solving from some initial composition driven by stellar radiation to somewhat more complexity. In this study, we use diverse sets of M-star radiation, varying initial compositions of C2O ratios between 0.5 and 1.5, because this is a transition of where feedstock production might be supported or might not be supported, for 3 different background scenarios of CO2, where we then vary the amount of methane over the CO2 to create these C2O ratios. Vulkan comes with a standard chemical network, and these plots may be a bit overwhelming, so I don't expect you to read every species here. The NCHO network has 70 species, connected by 470 reactions, treats oxidizing to reducing conditions. In hydrocarbons specifically, it goes up to benzene, but you can see from the hydrocarbons in the top right here with a limited amount of reactions. Vulcan's network has been validated for Earth, Jupiter's, just Jupiter, and hot Jupiters. But then recently, there was also this so-called Kraken-O network published, which specifically focuses on hydrogen cyanide and formaldehyde chemistry and treats hydrocarbons up to ethane, as you can see over here. This one was validated for hydrogen cyanide production on Titan. So what we did in this study was to implement the Kraken-O network in Vulcan. And the first test, of course, is then to see what happens. So I'll show you a few vertical distributions of key atmospheric species. You can see that for a C/O ratio of 0.5, the networks do a reasonably similar job. But note that this is for the condition that no methane is present in the atmosphere. As soon as you add methane to the atmosphere, things get a little bit different. If you look at higher pressures here, so basically pressures higher than 10 to the minus 4 bar, there are some similarities between both networks, but especially in the photochemically active regions, lower than 10 to the minus 5 bar, we see a lot of differences. And notably, what Kraken-O produces is this solid purplish line over here, is a lot of ethane in the upper layers of the atmosphere, whereas NCHO instead accumulates this dashed yellow line, C4H3, along with a few other of the somewhat complex hydrocarbons. Now, why is this important? This is important because in Vulcan's network, as it is at the moment, ethane is a strong UV absorbing species. So what I show you here is the UV photosphere, which basically shows the pressure levels in the atmosphere at which the atmosphere gets optically thick to radiation at a specific wavelength. You can see for NCHO, if you focus on wavelengths around 125 nanometers, that the absorption here is dominated by methane and around this by CO2 and CO. In Kraken-O, on the other hand, since you have so much ethane production, this actually overtakes methane, it overtakes CO2, and in this way shields these two species from photolysis. And of course, this would affect the further balance of prebiotic feedstock species as well. As I said, in NCHO, you build up these C4 and C3 hydrocarbons that specifically are not treated as photochemically active. Therefore, you don't have the shielding mechanism in the NCHO network. Now, to show how this varies across different initial conditions, you can see that as a function of C/O ratio, there's an enhancement of ethane, and this shows the average Kraken-O abundances compared to average NCHO abundances. You can see that ethane is enhanced in Kraken-O as compared to NCHO for all these C/O ratios, and that this brings shielding of methane, CO2, hydrogen cyanide, formaldehyde along with it. Cyanoacetylene and acetylene are basically not produced in Kraken-O and therefore have a much lower abundance in Kraken-O as compared to NCHO. This holds for 400 ppm CO2 background, as well as for a 10% CO2 background. And in the view of time, I'm not showing you the test for all the different M-star types, but this holds across different M-star radiation as well. So we have this situation where in NCHO, these more complex hydrocarbons don't provide any shielding, and therefore you have lots more photochemical dissociation of your prebiotic feedstock molecules, whereas this layer of ethane in Kraken-O protects anything below them. Now, of course, since we have equal physical settings between both simulations, these differences have to come from the chemistry. This has been quite a pain over the years. But so we've investigated the pathways between species. So in this case, using the Dijkstra's algorithm, where you basically find the shortest path from one species to the other, taking the reaction rates between those species into account. So it's similar to you finding the shortest path from here to the karaoke bar on Google Maps yesterday evening, for example. We focus on pressure levels that are related to the maximum hydrocarbon production. And then you can see for the NCHO network that following methane photolysis, you go through ethane production, acetylene production, but in the end, you have the edges of this network, you can see you build up these somewhat more complex hydrocarbons. Whereas in Krakenow, following methane photolysis, what you end up with is this loop of the C2 hydrocarbons. And note that reaction strength is shown here by the width of these arrows. So the reaction towards ethane is the strongest, and therefore you build up ethane in the Krakenow network. Now, this means that for NCHO, you have a lot slower hydrogen cyanide mixing ratios than for Krakenow. And note, as compared to earlier work that has focused on hydrogen cyanide production, the Krakenow, what did I do? Okay. The Krakenow network matches these earlier predictions. Now, of course, there is a strong sensitivity to the physical environment. And if you want to learn more about it, I think there is a poster session still. I would suggest you check out Gergely's poster, because in the end, what you can do with these predictions of prebiotic feedstocks, you can connect it to a certain origin of life scenario, construct what is known as the abiogenesis zone, and see which of your planets fall inside of the zone. Now, the shielding mechanism that we found here adds to other shielding mechanisms of CO2, as well as hydrocarbons on the early Earth. But I do want to note that, of course, the fact that C3H4, C4H3 are at the moment not treated as photochemically active doesn't necessarily imply that they're not photochemically active, but more is suggestive of some missing cross-section data. And therefore, and even more so if you have these complex hydrocarbons, what you would expect in the end is to end up with hazes, which again can provide you potential shielding effects. So future direction of such research is to actually see if the shielding effects hold for treating all the photochemical cross-sections, as well as a potential haze formation mechanism. And I think this fits the point that these chemical networks at the moment simply express our knowledge of certain systems and not necessarily reality. So I'll leave up the conclusions. Happy to answer questions. Thank you.
Thank you. There, yes.
Hi, Ollie Shortall, University of Cambridge. I was wondering whether there's a potential tension between the accumulation of prebiotic feedstock by shielding the lower atmosphere from UV and the potential need for UV in aqueous solution to drive the prebiotic chemistry.
Yes, yeah, I definitely think so too, because, well, as in the previous talk as well, you would kind of need the 250 nanometer wavelengths to drive any further complexity deeper down in the atmosphere. And I can go back. Yeah, sorry, it was quite insane, those pages. And you can see that, I mean, it's not even shown here, but not a lot of radiation of these wavelengths ends up at the surface if you consider all the atmospheric photochemistry that is going on. So yes, I would totally agree.
Okay, then we first have a question online, and then we have you in the back.
Thank you. Another anonymous attendee. Can you talk a bit more about the advantage of 3D modeling over 1D for understanding prebiotic plausibility?
Yes, absolutely. So maybe this fits the point of where you have these shielding effects, because of course in your 3D structure, any gaseous species, but especially any haze species, won't be uniformly distributed. So you might envision a situation where you have hazes in a certain location blocking out all the light, whereas in another location, you might not have your hazes, and the UV might actually pass through the surface. The second advantage is the fact that in a 3D model, you have the most accurate prediction of any precipitation, linking the photochemistry in the atmosphere to any surface processes. And the third reason is that, especially in the context of tightly locked planets, we know that there is circulation mechanisms that connect photochemical regions with photochemically inactive regions. So in that sense, even hazes that you might produce on a day side hemisphere, say, might actually end up just precipitating out all of them on the night side hemisphere.
Okay, last question. Yes.
Hello, Gwenaël van Overen of the University of Vienna. I wanted to ask, what were your assumptions on the thermal pressure profile?
So I don't know if I have it now. I'll just say, so I used predicted GCM temperature pressure profiles for Proxima Centauri b. So this was one of the host star types that I have included, which were consistent with the 400 ppm CO2 case. So they were not consistently calculated for the 1% CO2 or the 10% CO2 case. So it was just fixed to that settings.
If I may add a quick addendum to that, up to what or down to what pressure do you go?
So it's 5 times 10 to the 8,
Nice.
10 to the minus 8 bar.
Thank you.
Okay, thank you very much. Before we thank the speaker again, we have a coffee break until 11:20. Thank you.
Please take your seats. Welcome back, everybody, from your coffee break. Please take your seats. Welcome back from your coffee break. My name is Floris van der Tak. I'm happy to chair the final session. Our first speaker is Marilou Fourier-Tendreau from Oxford.
I'm Mary Lou. I'm a PhD student at the University of Oxford. I'm working with Ray Pierrembert, and today I'm going to talk about the tectonic controls on seafloor weathering. So let's start with the silicate weathering feedback, which is thought to have played the role of a geological thermostat on Earth. So for those who are not familiar with silicate weathering, it's the reaction between silicate rocks with water and carbon dioxide that eventually leads to the formation of carbonates. So it's a carbon sink in the carbon cycle. And it is believed to balance the outgassing of CO2 by volcanoes. So if you have a planet that is warming up, you would expect the silicate weathering rates to increase so that the consumption of CO2 increase, and then the planet can cool down. So this is actually this negative feedback that underpins the concept of the habitable zone. So as stars are increasing in luminosity, you would expect the silicate weathering rates to adjust so that the surface of the planet stay temperate. But the carbon sink also happen in the seafloor. So actually, the seawater circulates through pores and fractures, and this is driven by the heat advection from the plate cooling. And as the seawater circulates through the crust, it alters the basalt, it releases calcium cation, and it increases alkalinity. So all of this promotes the carbonate precipitation. So the idea is that changes in bottom ocean temperature could drive global weathering rates. However, there are arguments to think that seafloor weathering is supply limited because you don't have erosion as on land where you can have fresh minerals bring to the weathering zone. So there are also arguments to believe that the seafloor weathering rates depend on the formation of new crust. So for Earth, we believe that's the silicate rocks on land that have played the role of this buffer of climate. But for seafloor weathering, it's highly debated. We're not sure how much seafloor weathering can buffer atmospheric CO2 over billion-year timescales. And it has huge implications for ocean-covered rocky exoplanets. But there is geological evidence for seafloor weathering to have been playing the role of a thermostat. And if we look at the measure carbonate, so the CO2 in the oceanic crust, the crust that was formed during the late Mesozoic has nearly 5 times more carbonates than the Cenozoic, and the late Mesozoic was known for being a hot house climate. And we do expect seafloor weathering to happen primarily in young crust. So you wouldn't expect over time to keep accumulating CO2. So my work was actually to investigate the controls on seafloor weathering with this new model, the Mayen-Chamberlain framework. So this weathering model regulates climate and tectonic forcing through hydrologic processes, so making it very relevant to the oceanic crust. So it couples different weathering limits, so the kinetic, sorry about that. So the kinetic, the temperature-driven weathering, it also takes into account an equilibrium limit, and it also takes into account a supply limitation that will happen over time if you don't have efficient erosion. So, sorry. So this model is way more mechanistically accurate than the conventional way of modeling weathering rates, which is usually a product of the spreading rate and the kinetic dissolution of silicate. So my first step was really to adapt this Mayen-Chamberlain framework to the oceanic crust. So the first step was to account for a thermal model because the plate cooling is what induces the hydrothermal circulation. And the second step, and that's what I'm going to focus now, was to account for this age-dependent declines in permeability and in fresh mineral availability. So what happens is, as you get away from the mid-ocean ridge, the pores are filling by carbonates and, are filling by, the vesicles are being filled by carbonate and clay minerals. And there is also a mineral depletion that happens over time. So in this model, there is 2 parameters. There is the weathering zone age that depends on the availability of fresh minerals. And there is also the reactive flow path length that depends on crustal permeability and porosity. So I've taken this into consideration with new work. So this is Eventel. That's a paper that was published last year. And they realized that the crustal cracking that is induced by plate cooling, so the formation of brittle fracture, which shapes the hydrothermal evolution of the crust. So as you move away from the ridge axis, you have less hydrothermal circulation. And they found actually a correlation between the change in hydrothermal circulation and the change in cumulative strain. And you can scale the strain rate as a function of plate cooling. So I've introduced this in my model, as you can see here, for the reactive flow path length, but also for the weathering zone age, because if you have more cracks that are opening over time, you have those fresh minerals that are being brought to the weathering zone. And I have to mention as well, they also found that the late Mesozoic crust had more strain than the Cenozoic crust. So the second step for me was really to calibrate my model with the Cenozoic CO2 crustal content. So you can see here, my model offered a good fit to the functional fit of Gillis and Coogan. So I reproduced the observed crustal CO2 contents of the Cenozoic. Then, if I take into account the seafloor age distribution, I reproduce as well the present-day global seafloor weathering rates, which is 0.5 T-mole carbon per year. So all of this modeling is really interesting to look at the different weathering limit in the seafloor. So what you can see is as you move away from the mid-ocean ridge, you start by being kinetically limited. So your temperature-driven weathering is happening, if you take the seafloor age distribution, in 10 to 15% of modern seafloor. And then after this, you become supply limited. So the last step for me in my model exploration was to try to reproduce the elevated CO2 contents of the late Mesozoic. So the first step I've done, it was to increase the bottom ocean temperature, because for the late Mesozoic, we expect to have around 12 degrees higher temperature at the bottom ocean. But actually, this increase in temperature only increase the weathering rates by 2 times. And this is lower than what is expected in classical models, which is a 5 times increase. And it is not reproducing this higher CO2 contents. So after that, what I've done is to increase the strain rates. So now, if I take into account this maybe higher strain rates in the late Mesozoic crust, I can finally reproduce the elevated CO2 content. So this would be an enhanced exposure of surface reactive area in the young crust being formed in the late Mesozoic. And one hypothesis for this, it might come from the increased plate coolings that have been reported at mid-ocean ridges following the Pangea supercontinent breakup. And finally, if I take into account the age distribution of the seafloor in the late Mesozoic, which is thought to be younger because of higher spreading rates, then I have a global seafloor weathering rates of 8 times the present day. And you remember, I had the 2-time increase with elevated temperature at the bottom of the ocean. So my takeaway message is that tectonics exert a first control on the global seafloor weathering rates. And also, the temperature dependence of seafloor weathering is weaker than what we usually think with the conventional model that only depends on the kinetic of seafloor weathering. So what it means is that potentially seafloor weathering have played a limited role in regulating long-term climate. So my future work will be to explore this and look at the implication for ocean-covered rocky planets.
Perfect timing. Thank you very much. Who has a question? Online question, maybe? Yeah.
Hi, Sarah Rukheimer at Edinburgh. I was just wondering, did you also take any look at like planets that maybe are only stagnant? They only have like hotspot volcanism. Is that like an area you're planning to go into on like how long those planets might be able to buffer climates? Do you have any like intuition as to that?
Yeah, that's a really good question. Actually, I started with the plate tectonics because I wanted to try to constrain in some ways seafloor weathering for at least one planet that we know, but definitely, and Ray would really like me to, after that, explore stagnant land. What would happen if you don't have this like crustal evolution and subduction? And yes, so future work.
More questions? Well, let's thank our speaker again. And our next speaker is Guillaume Chavarot from Grenoble.
Hello everyone. My name is fellow and illustrating this presentation, I'd like to discuss a little bit about the concept.
Yeah, okay, this is better. Sorry. So yeah, I'm gonna discuss a little bit the habitable zone concept that other people introduced this morning. And I would like to try to discuss with you the influence of hidden parameters and especially the planetary parameters such as the atmospheric composition. Okay. Yes. So first of all, just to be on the same page, I'm gonna talk about the old definition of the habitable zone that is actually not super new and that has been developed for the solar system and especially to try to understand differences between the Earth, Mars, and Venus. And here, the definition is only the capability of a planet to sustain liquid water at the surface. So this was the initial definition, but as we discovered many planets, we would like now as a community to try to use this concept to have a population study and if possible to try to select a relevant target for future characterization and to try to discover liquid water at some point. So starting from this, we can use the famous definition proposed by Koparapu to calculate the inner edge and the outer edge of this habitable zone, defined thanks to the flux received by the planets and for different stellar types. So here is the habitable zone. Here you are too hot and the planet is in a post-Noah state. And here the planet is too cold and the water freezes at the surface. So this definition has been made for the Earth, so the Earth's size, mass, and atmospheric composition. But thanks to climate modeling, we can modify the atmospheric composition. For example, considering H2 in the atmosphere. And if you do this, you basically shift a little bit the habitable zone outward. You can also, for example, change the CH4 to CO2 ratio, and this affects mainly the outer edge of the habitable zone. So this is 1D modeling, but we have also more complex 3D models, and we can also vary the atmospheric composition with those advanced models. So again, if we change the H2 content of the atmosphere, same trend, you push the inner edge outward. And if you increase, for example, nitrogen, the effect is the contrary. And when you increase nitrogen, you extend the habitable zone toward the star. So what I want to show with this figure is that we already know, thanks to the papers in the literature, that atmospheric composition has a strong impact on the size, on the position of the habitable zone. And as you can see, varying this induce a variation of the position of the inner edge that is almost as big as the size of the habitable zone in itself. So when studying, when using this concept to study large sample of planets, we cannot just assume that this is the atmosphere of the Earth. It's a little bit more complex than this. The issue is, if you want to do climate modeling with a lot of different atmospheric composition, you need different opacity data to calculate relative transfer within the model, which is not easy because we showed a few years ago that you cannot just mix opacity data of pure spaces, put that in your model and have a great calculation. If you do this, you have errors in the calculation that are really important, especially for the inner edge of the habitable zone, so for the calculating the runaway greenhouse. So I spent quite a lot of time discussing with people doing a spectroscopy lab experiment to try to update data, especially for CO2, for different mixture of CO2 that are relevant for terrestrial planets. So we basically took the lab experiments, calculating new empirical correction factors to be able to calculate accurately high resolution spectra for those mixtures. So we calculated different quality tables and also created a continua of CO2 mixture. So if you do climate modeling, this could be interesting for you, including for magma ocean modeling. So thanks to this, we calculate the inner edge of the habitable zone with a simple 1D model. So here you have the inner edge, so defined as the insolation received for different planetary masses. And as we know since this paper, if you increase the mass of the planet, you extend a little bit the habitable zone. And we show that this trend is true for every kind of stars and for every atmospheric composition from very thin to CO2 dominated. So this is the first test we did. Then we varied the atmospheric pressure, again, for different atmospheric composition. And basically, what we see is that beyond 2 bars of atmosphere, there is no real evolution of the position of the inner edge. But for very thin atmospheres, you extend a little bit the habitable zone toward the star, which is another interesting trend. And finally, we also varied the CO2 content in the atmosphere. So started from a terrestrial composition to a pure CO2 atmosphere. So in this case, the trend is a little bit more complicated, as you can see. And we understand this as a kind of competitive effect of CO2 between the greenhouse effect of CO2 and the Rayleigh scattering induced by CO2 when the atmosphere is CO2 dominated. So that's why we have a kind of weird trend here. And finally, if you mix all those calculations, saying, okay, we in the best case, we know the mass of the planet, the radius of the planet, but it's super difficult to know the atmospheric composition. So it's kind of a hidden parameter when you do population study. We calculated again the habitable zone for different stars, and this area is basically the uncertainty we have on the inner edge of the habitable zone induced by those hidden parameters. So here I put the tidal locking time of the planets for around M dwarf, and as you probably know, for tidal locked planets, the climate is quite different, and 1D model are not relevant enough. And if you use a 3D model, you have this inner edge for the habitable zone. So this calculation using 1D model is most relevant for K dwarf and G dwarf. So my point here is that, as you can see, those hidden parameters induce an uncertainty that is almost half of the size of the habitable zone itself. So we should not, when using this concept, we should not consider just a planet within or without the habitable zone, but must saying, okay, if your planet is in this area, it's very likely to be able to sustain liquid water at the surface. If it's here, it's absolutely not likely to sustain liquid water. And in this area, the planet could sustain liquid water if the planetary parameters are good, I would say. So here I discuss like optimistic and conservative habitable zone. It's a terminology that exists in the literature, but just a side note that when you see optimistic habitable zone, it's often linked to the runway, the recent Venus limit, which has been proposed 3 decades ago, supposing that Venus sustained an ocean when it was young, but this is highly debated today. So you should not use this definition anymore. Okay, and yeah, if there are observers in the room, I think there is a sweet spot for massive planets around K dwarf, because here the habitable zone is super large. And I'm gonna conclude with a few interesting points, and I don't know what's up. Okay, maybe an update. Thank you very much.
Excellent. 20 seconds too fast. First question right here.
Hi, Mara T, Captain. Thanks for the great talk. I was wondering also about like the uncertainty that could be like an additional uncertainty provided by the equations of state. Actually, like, do we know like what's the size of the uncertainty that can be added to like those hidden planetary parameters and the opacity tables you mentioned?
That's a good question, but oh, doesn't move. Can I switch back? Okay, perfect. Thank you. Yeah, it's an important point, but it's definitely a second order process compared to this, because as you can see, if I come back on the spectroscopy, yeah. Those lines are the new updated correction parameters we have for CO2, and here are the old parameters. So for some mixture, it's kind of a big difference, but between the windows. So compared to changing the atmospheric composition, this is a second order process, and compared to this equation of state are third order process.
Marek?
Hi, Guillaume. This is Marek from Bern. When you take the habitable zone limits for tidally locked planets, I assume you mean one-to-one resonance, right?
Yeah.
Would this change a lot if you take other possible resonances?
Like 322 or stuff like this?
For example.
That's a good question. I think, if I remember correctly, the paper of Koparapu, this one, it's pretty close from a climate point of view between 1-to-1 and 3-to-2. It's like slow rotating planets versus the rotation of the Earth. So I suppose, so it's mainly important for this transition because this is like super tidally locked, but between here, this tidally locked limit and this 25 hours rotation limit, we have a kind of continuum of rotation, and we don't know it's in the question from a system to another. So there is here like a gray zone, which is difficult to understand for now. So you have to focus on a specific planet.
Any online questions? No? Final question then? Can the next speaker come up?
Thank you. Evelyn McDonald, University of Vienna. I was wondering, so you talked about Rayleigh scattering having a nonlinear effect on the size of the habitable zone. Could you explain why that applies also for M dwarfs, where Rayleigh scattering is so much less important than for G dwarfs?
That's a good question.
How it applies?
That's a good question. So even if the Rayleigh scattering is less important, it's supposed to be there at least a little bit. So I think this effect is, there is still this kind of competition. Yeah, I mean, it's how we understand the result so far, but we still have to discuss. So if you have any opinion about it, I will be happy to discuss, of course.
Yeah, I don't know the answer. Just interesting.
Okay, thanks.
Thanks.
Thanks very much again. And our next speaker is Akihiro Kamada from LZ Tokyo.
Okay. Can you hear me? So I'm Arihiro Kamada from Institute of Science Tokyo. Today I will talk about the application of global climate model for early months to exoplanet. In addition to the high resolution, sorry. Thank you. So in addition to the high resolution global cloud resolution model talked by Dr. Kodama in this Wednesday, so in our laboratory, we conducted early Mars and early Earth and other exoplanet GCM in our laboratory. And to date, more than 6,000 exoplanets have been discovered in our neighborhood, and most of them are orbiting around the M-dwarf stars. And planets in the habitable zone around M-dwarf star are tidally locked, and they have a permanent day side and night side. Previous GCM studies for tidally locked exoplanets have focused on the atmospheric circulation, so they did not consider about the surface river runoff and ice sheet flows. So this calculation lead to the idea that all the day side water evaporated and they are transported to the night side and accumulated in the night side. So however, to understand the global water cycle on tidally locked exoplanets, so we should consider the full water cycle between atmosphere, ocean, and land that includes the surface river runoffs and ice sheet dynamics. So however, it is difficult to convert our Earth GCM to directly to the exoplanet GCM. So in this study, to bridge the gap, we used the early Mars GCM as a test bed case. Because the early Mars, so in the early Mars, there are many lots of water-related surface landscapes, such as the river systems and ice sheet landscapes. So yes, so we use the early Mars as a test bed. In the Earth GCM, it is included the atmospheric dynamics, water-related physics, and radiative transfer, and we integrated the additional river flow model and ice sheet model to the Earth GCM, and finally, we assumed the exoplanetary orbital parameter, and we calculate the exoplanetary climate. This is a so this is a description of our Earth early Mars climate model. So in our model, we used the Japanese global climate model named Miroku. And we calculate this early Mars climate first, assuming the 2 bar CO2 atmosphere and additional greenhouse warming gas such as hydrogen. And we assumed early Martian solar flux of 441, that is 1/3 of the present day Earth. And we calculate the very long time scale of water cycle on early Mars for 120,000 years. And then we calculate, this is the result of early Mars climate. So when early Mars contains higher concentration of atmospheric hydrogen, so this hydrogen is a very strong greenhouse effect. So during the 100,000 years, early Mars maintains a very warm climate. And so ice sheet only formed in the mountainous regions, and surface river activity is very active. And so in this warm situation, early Mars experience very simple water cycle. That means from ocean, water evaporated from the ocean, and this water vapor advected to the land region, and it falls as a rainfall, and they return back to the ocean as a river flow. And in addition, we calculated the cool early Mars climate. That means that we assume the lower concentration of hydrogen, 3%. And in that case, early Mars would be relatively colder climate. So that means surface temperature is slightly below the melting point of water. And in low to middle latitude of early Mars, there are very thick ice sheet, can be formed at the 2 or 3 kilometer thickness. And even in the case, this ice sheet can be melted beneath the ices due to the geothermal heat flux, and this melted water is a water source for river flow. And in this cool early Mars situation, water sublimated from the frozen ocean, and water vapor is advected the land region, and it falls as a snowfall. But this snowfall can melt due to the geothermal heat flux, and this meltwater flow back to the ocean, and so that water cycle can be closed even in the cool early mass. So we can validate our water cycle model for early mass. So then we move to the exoplanetary GCM simulation. So in this calculation, so we assume the tidally locked planets, and we assumed very simple topography. And that means day side ocean and night side land. In this study, so we assumed a very simple 1 bar CO2 H2 atmosphere and the solar intensity of 879 watt per square meter. And so we calculate the full water cycle between the atmosphere, land, and the ocean, including the river runoff and ice sheet flows. And this is the result for animation results. So this means the surface temperature. And so in the 1 bar CO2 atmosphere, so dayside region can be very warm. And even in the night side region, so the surface temperature is relatively warm, but in the downside region, surface temperature is below the melting point of water, so it's environment promoting the snowfall. And this is the zonal wind flow, so it has in this exoplanet system, so there is a jet flow in the equatorial region above the 50 meters square. And this is a cloud results. So in the day side and dawn side, there is dense cloud exists, but in the dusk side, there is almost no cloud. And this result is rainfall, snowfall. So yeah, so in the dayside region and downside region, there is a lot of rainfall. And if in the dayside region, so the rainfall rate is above 10,000 millimeter per year. And in the snowfall results, so snowfall can only occur in the dusk side region because this surface temperature is below the melting point of water. And so this snowfall forms the ice sheet. So this ice sheet grows year by year. Year by year. And after 1,000 years simulation, this ice sheet can be accumulated up to 1,000 meters thick. And this ice sheet and this rainfall produce the surface river systems. And so even in the night side, so liquid water can exist, and liquid water from the river and flow back into the dayside ocean. So even in the tidally locked exoplanets, so water cycle can be closed. So yeah. So how does the water cycle on tidally locked exoplanets? So it is probably long. That means in the tidally locked planets, so water evaporated from the ocean, only accumulated in the night side and never long. Back to accumulated in the night side is very long. Probably from our simulation result, the water cycle can be closed. That means water evaporated from the ocean and it is back to the night side, and it falls at the rainfall or snowfall. But this snow can be melted and back to the ocean. So water cycle can be closed in the tidally locked exoplanet. That is all. Thank you.
Thank you very much. We have time for a couple of questions. Who wants to start? Yeah?
Thank you, Madeline Broom, UC Santa Cruz. Can the humidity gradient created by evaporation drive any sort of meridional flows like winds around the planet?
Sorry?
Can the humidity gradient created by evaporation over the ocean drive a pressure gradient that can drive winds around the planet?
Yes, so this is the global wind field in the 250 hectopascal. And that means so equator region, so jet wind can be occurred, but in the night side region, so what wind does not circle. That means so gyre structure can be formed. This structure so can be produced by the temperature gradient, and so yeah.
More questions? Yeah.
Hi, Tad Kamasic, Oxford. So about your tightly locked rocky planet simulations, can you explain what generates the topography in them? So do you have a land map? And if so, what do you assume about that land map? Or is the topography generated by the sea ice itself?
So in this study, we assume the very simple topography. So artificial day side lowlands and night side highlands. So, but this climate regime probably would be different if we assume very different. So that means the day side highland and night side lowland. Yeah.
Yeah, and then is there a slope on the night side?
Yes.
Or is it flat? Oh no.
So we set the artificial slope. So that means that the night side region, the 1,000 meter altitude and minus 1,000 meter altitude. This is very artificial topography.
Online question, maybe? Final question, yeah.
Hi there, William Brilliant, University of Cambridge. Is there ever a scenario where snow, say, accumulates on the night side, eventually in locations where there isn't any geothermal heating, and then does the water cycle cut off and everything just stays on the night side? Is that possible in this simulation?
Sorry, what do you
mean? Is it ever possible that you end up in a steady state where just by chance the snow has fallen where there isn't heating and it doesn't flow back to dayside?
So if ice thickness or increase year by year, so the geothermal heat flux can melt subglacial ice, and so in the finally, so water equilibrium can be achieved. So the snowfall rate and the subglacial melting rate probably finally equilibrate.
And then are you assuming like a uniform geothermal heating?
Yes, so in this study, we are the 100 milliliter per square, so geothermal heat flux.
Okay, fine.
So probably this value is very important for subglacial melting.
Thank you again.
Thank you.
And the next talk is by Kevin Franz from Colorado.
Right. Great. Yep, I think so. Okay. Thank you. Good afternoon. Kevin Franz from the University of Colorado. So I'm going to tell you today about the Habitable Worlds Observatory. This is NASA's next flagship mission to launch after the Roman Space Telescope, which is expected to launch later this year, maybe beginning of 2027. One of the nice things about giving the second to last talk in a meeting is that I don't need to do a lot of introduction. So I'm just going to jump right into what is the Habitable Worlds Observatory. So this was the top large mission recommendation in the US Astro 2020 Decadal Survey. This is the first telescope specifically designed to search for signs of life on rocky exoplanets beyond the solar system. If we were at a different conference, I would also be telling you about all the transformative astrophysics and basically all the other areas that the mission will be able to accomplish. You can sort of think about the Hubble Space Telescope times about 100. But for this meeting, we're going to talk about the search for rocky exoplanets. Now, at this meeting, we've heard about secondary eclipse observations. We've heard about transit spectroscopy, a little bit about reflected light spectroscopy, and that's the technique that HabWorlds uses, where it uses the technique of high contrast imaging to block out the bright light from the central star and take images of the field around that using a coronagraph. So this is a simulation, a time-lapse simulation, observing the solar system at 10 parsecs over the course of 10 years. And you see the planets come in and out. You see the colors of the things as they go to the edge of the field. That's the wavelength dependence of the outer working angle. And so this is the technique that HabWorlds is going to be using. It was mentioned earlier that this is very challenging, and that's correct. The star-planet contrast for an Earth-like planet is about 1 part in 10 to the 10. This means we have to throw out 10 billion stellar photons for every 1 planetary photon that comes in. It's actually also very challenging because the brightness of an Earth-like planet at 10 parsecs is a V magnitude of about 32. And so for those of you who have ever observed things on the sky, that's very, very faint. So this is going to be challenging to not only do the starlight suppression at that level, but also have enough collecting area to do that. So the mission will essentially search over 100 nearby stellar systems to find family portraits like this. And once we've identified those family portraits, we'll put some sort of an integral field spectrograph behind that coronagraph to take low, medium resolution spectra. And this is a predicted spectrum from, again, that same Earth-like system at 10 parsecs with realistic error bars. So what are we looking for? A lot of the things that we've heard about today, the signs of water vapor in the atmosphere. Water itself is not a biosignature, but we think it's probably a signature of an habitable environment. Looking for molecular oxygen and ozone. And then depending on the type of life and the phase of the evolution of that planet, you might be looking for things like methane. So one of the take-homes here is that this is a pretty broad wavelength coverage. And you need that broad wavelength coverage not only to capture all of these spectral features, but to be able to understand how the planets you're looking at are evolving in time. So if we want to take this as essentially the same spectrum that I just showed you, this is the reflectance spectrum of modern Earth. But this only covers about 10% of Earth's inhabited history when the O2 abundance is relatively high, pretty close to present-day limits. If you roll back the clock a little bit and ask what did this reflected light spectrum look like earlier in Earth's history. So here are 2 spectra when after the Great Oxidation event, but not when Earth was at its present-day oxygen levels, where the O2 levels were down maybe 1% or even sub 1% of the present day. So in those times, the oxygen A band at 760 nanometers becomes very challenging to detect. But now ozone is no longer heavily saturated and can become a very sensitive proxy for the total oxygen abundance in the atmosphere. But you only get all of these things by having the relatively broad wavelength coverage. In addition to that, I mentioned that these are faint, so we need a telescope size, not just to be able to detect faint things, but also because the telescope size drives the inner working angle. So it's been studied extensively as the lead up to the US Decadal Survey. With a 4-meter class telescope, you get something like 8 candidates. If there's a 10 or 20% chance of those rocky planets having active biospheres, you might not find any. And so what you've really learned from a non-detection there is that you wish you had bought a bigger telescope. So with a larger telescope, 7, 8-ish meters, you'd be able to access about 25 rocky Earth planets. And you need something like a sample size like this to have a 95% confidence that you'll be able to find an inhabited planet, something that shows the signs of biosignatures. Okay, so you're all familiar with the scientific motivation for this. So really my motivation for coming to give this talk was really to kind of give you an update on what's happening with the Habitable Worlds Observatory, and also, if you're interested, how you can get involved. So here's a very simple, not NASA-approved timeline of how this process has gone. So in the US Decadal Survey was released in 2021. In January of 2023, this was adopted by NASA as the thing we now call the Habitable Worlds Observatory. There were some initial study teams that ramped up in 2023, and the science working group started in 2024. Now, the response to these science working groups was really pretty spectacular. So what started as a relatively small number of people, we'd have meetings about every 2.5 months, and every time we would have another meeting, twice as many people would come, and this kept happening, and eventually over 1,000 people contributed about 75 very detailed science cases for HWO. This is not just on exoplanets and all areas of astronomy. But these are sort of 10 to 20 page, some of them pretty deep dive science studies that form the basis for the supporting the general goals that the decadal survey laid out. So that process has happened now. In late 2024, there was an official project office set up at Goddard Space Flight Center. That's the same way that we do with, say, the Hubble Space Telescope or JWST. So this is a real mission now. And then in mid-2025, the community science and instrument team and what we call this cross-PAG science interest groups were stood up. Let me just say quickly what those are. So this community science and instrument team, this is the group that's actually working with the project office directly to identify the driving science cases, review and analyze the instrument concepts, develop level 1 mission requirements, and also be the outreach to the community. So if you have questions about HWO, want to understand how you can get involved, or would like somebody to come talk about details of HWO, please you can reach out to me or reach out to any member of the CSIT, and we're happy to engage with that. If you're interested in getting involved in the preparation for the science analysis of the mission, there's the newly stood up science interest group, the SIG, right, with NASA. It's all a bunch of acronyms and things that are really complicated. So this is the cross-PAG SIG, and almost all of those words are acronyms for something. So these are the folks that are doing supporting science data analysis for the mission. And I put the QR code there for these different areas if you want to get involved. All right, looking to the future, there'll be instrument concept studies that are happening later this year. There are 3 baseline architectures for the missions that have been studied already. We call these exploratory analytic cases, or EACs. If you notice there that the telescope mirrors look wavy, they won't be like that in real life, I promise, or I really hope. So these are the first 3. There's 8-meter on-axis and a couple of 6-meter designs. Those are now moving into 2 more designs called EAC 4 and 5 that are exploring apertures as large as 8.5 meters, which is really exciting. So those instruments, or those telescopes, are supported by 4 instruments. There are 4 instruments that are in the baseline mission right now: a coronagraph that we talked about already, high-resolution imaging camera, multi-object UV spectrograph, and integral field UV spectrograph. And then there is a 5th instrument bay that will be basically explored for international contributions. And with that, I'm pretty close to running out of time. So what I want to do is just leave up the sort of final slide here that also has the QR code if you're interested in getting involved in the science analysis again. And I'm happy to take any questions. Thanks.
Perfect timing. Lots of time for questions. Yes. Here in the front.
Hi, Kevin. This is Laura Cradberg from MPIA. Can you say a little bit more about plans to coordinate with the radial velocity community for target finding, what the status of that is?
Yes, great question. So masses for these planets is obviously a huge thing. So there has been a fair amount of radial velocity coordination already. There is a precursor science program that exists within NASA right now. And it's expected or anticipated that it will be expanded over the next 2 years to have a specific RV component. There's also a lot of effort. One of the motivations for that high-res imaging channel is to be able to do micro arc-second level astrometry, to be able to get the masses second way, because we actually think that Not all of these star-planet systems will be amenable to good masses from radial velocities. But if we can do, I think the calculation, Scott Gaudy's leading this work, something like slightly less than micro-arcsecond astrometry, which we think is feasible. Challenging, but feasible. It's another way to get the masses. So there's a lot of effort to make sure we understand what the masses of these planets are.
More questions? Yes.
Hi, thanks for the talk. Rob Calder, University of Cambridge. So with Hubble and JWST, the mission aims across astrophysics have been fairly broad, but with HWO, the name seems to suggest specialization for exoplanets. So my question is, how much of the time and energy of HWO will be focused on exoplanets, particularly Earth-like exoplanets, rather than other fields of exoplanets and astronomy in general?
That's a great question. And this is the first time that I've gotten that question at an exoplanet talk. Normally I get it at an astrophysics talk that says, what's up with the name? Does this mean our science isn't included? So no, it is an observatory. The observatory is really the big thing here. The exoplanet survey is probably 40 to 50% of the prime 5-year mission. That's a guesstimate based on the predecadal studies like LUVOIR. And we expect it'll probably be pretty similar here. So it will be the largest single science case that's carried out by the mission, but it's definitely not like a 90% exoplanet discovery mission. You asked about, there was another part of the question in there that it is also the hardest part of the mission, doing the technology to do ultra-stable mirrors, to work on the high contrast imaging. So it does drive the majority of the technology development to facilitate the instrument too.
Any online questions? And for one final question. If not, let's thank Evan again. And the final talk in this session is by Evelyn McDonald from Vienna.
Okay, can everybody hear me? Excellent. All right, thank you all for sticking around. My name is Evelyn, and I'm a postdoc at the University of Vienna, working on the EASE project with Kristina Kysliakova. So this project is looking at early Earth, Venus, and Mars as exoplanets. And to start that, I'm looking specifically at the question of what Earth and Venus in their present state would look like with HWO in reflected light. Great. So our goal here is to be able to find and characterize Earth-like planets. And people have different opinions about what an actual Earth-like planet is and how we define a planet as Earth-like. So the most obvious things are bulk parameters, the stuff that we can observe the most easily, like the size of the planet, like its composition, as in a rocky planet, and an equilibrium temperature more or less the same as Earth's. Unfortunately, Venus also fits these criteria despite being nothing like Earth in climate. So it's these bottom things here that I'm really interested in being able to understand. So stuff like what's in the atmosphere, what are the surface conditions like? And so in particular, Venus has a much thicker atmosphere made predominantly of CO2. It is not habitable. It is very hot at the surface, and it has clouds made of H2SO4 primarily, which is not great for us as life forms. So I would like to know, if Earth and Venus were exoplanets, would we be able to tell them apart? So to answer this question, I've been using Earth data from MERA-2, which is a reanalysis data set of Earth in quite high spatial and temporal resolution. I've selected for this presentation data from September 2019, not for any particular reason, just to have like one day that's more or less in the middle of the year, not at a seasonal extreme, but this is kind of an arbitrary choice. On the Venus side, I've been using the Venus Climate Database, which some of you may be familiar with. It's a project at LMD from the Venus PCM and validated against observations. And it's a database of Venus 3D GCM data that everyone can access. And so I've been accessing these data to make spectra. So I'd like to start by, before showing spectra, explaining some key climate differences that we would like to be able to identify on these two planets. As we know, Earth and Venus are very different. Here's some MERA-2 data showing Earth's surface temperature at a particular time. And I just like to, as a GCM person, I just like to admire the resolution of these data. This is very nice. But perhaps more relevantly, the point I'm trying to make here is that we have substantial equator to pole temperature differences. We have land dependence in the surface temperature. We have circulation. You can see the effects of the circulation on the temperature as well. And we have surface liquid water. Venus, on the other hand, these data are slightly lower resolution. This is from the Venus Climate Database. There's much less of a difference between the equator and the pole and between day and night. It's very hot at the surface, pretty much everywhere. And of course, there's no liquid water. And so this difference in the spatial coverage of the temperature is due to the fact that Venus has a much thicker atmosphere and also that it rotates much slower. So it's able to redistribute heat across its entire surface. If we look now at the vertical structure of these two atmospheres, each line here is at a different latitude and longitude on the surface of the planet and going upwards, so one column of the atmosphere. I've done the same thing for the two planets, but you see a lot more lines for Earth because they're way more spread out. And this is again because of the spatial temperature differences that we have. You can also see that there's a thermal inversion at the bottom in some cases, another inversion up here in the stratosphere, and this very distinctive Earth-like structure of the atmosphere. Venus doesn't have that. It's much more homogeneous, pretty much the same everywhere. And this is an important difference between the two. So now coming to what observations we might be able to do. There's been a lot of discussion here about observations of rocky planets with transit spectroscopy orbiting M dwarfs. We've also seen a lot of flat spectra, a lot of non-detections of atmospheres, because these planets are so vulnerable to atmosphere loss, and also possibly because these measurements are so difficult. If we want to look at transits of an Earth-like planet orbiting a sun-like star, like what you can see here, first of all, it actually has an atmosphere, so that's great. However, we really aren't going to be able to see anything because the star is too big and too bright, and the contrast is too low. So that's the motivation for using reflected light instead with an instrument like HWO. So as we just saw, HWO is able to observe systems like ours in reflected light. So this example here is just showing that Earth and Venus would be visible. They're far enough from the star that the coronagraph doesn't block them, and they are detectable. Earth is a bit fainter, but it should be detectable. So to make these spectra, I've been using GLOBES, which is the 3D data model of NASA's PSG, the Planetary Spectrum Generator, which handles really nicely the spatial binning of 3D data and samples the entire disk. So here focusing on direct imaging modeling, but you can use this for transits as well. And I have a few test cases that I'd like to show. This is preliminary work. These are very preliminary data, so take this with a grain of salt. But here is a figure showing spectra of Earth and Venus. You can see that there's quite a difference. In particular, I'll draw your attention to this feature here, where Earth blocks a lot of light due to ozone, and Venus has this feature here of a distinctive shape from SO2. Venus is also just a lot more reflective in general. And then I took this same data set and changed a few parameters, not consistently. Like I didn't rerun a climate model. I just changed things like the surface composition. So a lot of us use aquaplanets in our simulations because they're the easiest or most straightforward thing to model a lot of the times. And I'd like to highlight the fact that water is not that reflective sometimes. It has quite a low albedo. This is not accounting for ocean glint, which is a whole other topic, but we have our aquaplanet here, not very reflective, not many strong spectral features, compared to a case with a reflective surface. I'm not sure what's happening here. Anyway, so what I did is just replace the water with snow, told the model that the surface is entirely covered with snow, and suddenly these water vapor spectral features over here are much more visible. The whole spectrum is much brighter. So the composition of the surface matters a lot. We also have a case here where I artificially reduced the amount of ozone in the atmosphere just to highlight the importance of this spectral feature at low wavelengths. This is also where the SO2 feature of Venus is. So really being able to understand the effect of these two molecules is going to be very important for telling these two planets apart. Another thing I'd just like to mention is clouds. Here's the same spectrum twice, once with clouds ignored and once with them sort of accounted for. As we heard in particular from Julia earlier, clouds are really hard, and the way that we model clouds is very important, has huge effects on the results. So really my point here is we need to account for clouds better, and that's going to be really important in our understanding of what these instruments can actually do. So that brings me to my conclusions. These two very different planets, we need to be able to understand the difference between them in reflected light with future instruments. We need to make sure we understand what's going on well enough to build instruments that can do this. And so as a next step, I will be working on improving the cloud model and accounting for instrument noise in this to see how best we can do that. So I'll stop here. Thank you.
Excellent. Thank you. Questions for Evelyn?
Hi, thanks for the super nice talk. Saumil Kelkar, Captain Institute. I'm just curious, are you also perhaps using the Meta-2 data to include, to model clouds for your Earth-like case?
Yes, sort of.
So
that can be done better.
right, so you also account for the variability in clouds, which is just naturally induced by weather patterns.
Yeah, so at the moment I'm using like a snapshot, one data point, but yeah, to account for the variability, you need to run it a bunch of times. There is a model in PSG for accounting for clouds developed by, I think, Vincent Kaufman, that basically like it like maximizes the cloud cover and then runs a cloud-free model and takes an average to try to match data better. But yes.
Thanks.
So a hand up there. Ooh, two hands. Let's.
It's Marek from Bern. So you showed that the latitudinal changes are not so big. Have you looked at longitudinal changes for Venus in particular and whether those would affect the reflected light?
Not specifically, like if we go back. Is this what you mean? Yeah, so these profiles are from everywhere on the planet, just color-coded by latitude. So there aren't as many changes. I focused on latitude because that's less time of day dependent, but yeah, I'm not sure how big of an effect that has.
Hi, thanks for the talk. Rob Calder, University of Cambridge. You talked about ozone in Earth's atmosphere and that being used to distinguish an Earth-like atmosphere, but Venus also has ozone in its upper atmosphere in similar concentrations to Earth. I'm just curious about how you think ozone on Venus might show up in reflected light with HWO.
Yeah, it is included in the spectrum. It's not the dominant gas that is affecting the spectrum, but it is included. So that is a good point, that if we had a Venus-like planet with more ozone somehow, that could be a source of confusion or a degeneracy between spectra as well.
All right, if there are no further questions, this concludes our final session. I would like to first of all thank very much the local organizing committee. They have done a great job running around with microphones, keeping the online program going and fixing all kinds of little problems. Thank you very much. And then right before the final announcements, can I ask everybody to stand up, please? Because there has been, so the LOC has done a great job, but there has been our single driving force, the single person without whom all of this would have never happened. I'm of course talking about the great Tim Lichtenberg. Tim, would you like to say a few words?
Oops. Just 5 minutes, all right? We'll soon go for lunch and then you can go home. Okay. Yeah, my voice is has some issues today, weirdly. So thank you all, really, very much for this amazing conference experience, and I really mean it. I think it was, I'm of course biased, but it was, I think really it was an exceptional event. It was amazing. The talks were of exceptional quality. I think it was really top-notch, state-of-the-art science. I think the program that we brought together at the conference was really, truly outstanding. And I think from my perspective, there's no conference which really mixes this blend of rocky world science, essentially, where we bring together astrophysics, geochemistry, geosciences, and climate sciences with lab experiments, observations, and theory. And so both the talk sessions and the poster sessions were really amazing. And I think what made this event special is really you. I really think the atmosphere was outstanding, and I really thank you so much for making this event really remarkable. And I will remember it for a very long time, and hope especially the SOC and LOC will do so too. Yeah. Here are a few impressions, actually, of photos we got. Please send further photos if you have. So we had many diverse events. So from our conference, and many of these group photos, the breakout sessions, and essentially all types of events that we had. I think that really made it possible that we talk to each other in both formal and informal settings throughout the conference. And I really hope that it gave also in particular the chance people who attended their first conference to really reach out to other people of the community and learn about, essentially get to know people. Maybe they have just read their names on papers and see their faces for the first time and talk to them. We have actually to announce the poster prize now. So thank you so much for everybody who voted for posters. And maybe let's give our poster prize winner like some I don't know, some noise. So who did it? Who got it? And Vasudha Trehan. Whoa! I want applause, please. Yes, please come down. Yes. Um, ah, Congratulations. We have brought you a little gift. And please, you can also unwrap it so that everybody can see what it is. And please, can Lynn come forward to take a picture with us? Actually, so thank you to Lynn also to organize this. This wouldn't have been taking place without her. Sheer will, I would say. Yeah. You can just yeah. 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 Yeah, so it's a popular science book, Alien Earth by Lisa Kaltenegger. So go on together. All right, let's take this. All right, or maybe on there. So then, yeah, let's stand here. Exactly. And also honorable mentions to the second and third place: Alfonso Mota, Prune August, Iris Buhr, Carmen Haukes, and Philipp Baumeister. Their posters, yes, exactly. Thank you, Lynn, for organizing this. Yeah, so very nice poster, and there are many other very, very outstanding posters, and I enjoyed to look at some of them and talk to many of you about it. Well, just time, really. So what made it possible, and I said it in the beginning and it needs to be said again, was really the support of our sponsors, the University of Groningen, who gave us these spaces for free, Esron and NWO, who were the major cash sponsors essentially for supporting early career researchers to attend this event, who were supported through the conference, and the Netherlands platform for planetary sciences. You have to clap a few more times. Let's do it one more time. Thank you. The SOC and LOC, here's the picture now with the people who were there. First of all, I really want to talk about the SOC. I think the SOC spent a substantial amount of time of really thinking about which talks or oral sessions we want to, oral contributions we want to select. We didn't make it easy for ourselves. And so we discussed a lot about this and spent a lot of time on this. And I think ultimately it worked well. And I think we had a very well balanced sessions, both the poster session and in the oral sessions. So let's please give a round of applause for the SOC. Yeah, and there are also some live action photos here at the bottom, but tiny so that it's not really recognizable later on YouTube, especially, you know. Yeah. But particularly important is actually, I think the LOC, there's even more live action down there. I think you realize the substantial amount of effort the LOC has put into this conference, where they are until now really like on it all the time. So we had always had a bit of a command center down here, and I think it really worked extremely well. There were some tiny hiccups sometimes, but these are unavoidable during events like these. And so overall, I think it really worked extremely well. Before we clap, please all come forward, the whole LOC. Please come to the stage, and Quentin as well. Yes. No. Because we have gifts for everybody. Ooh. It's the same. No, it's not. No, it's not. All right, so I need to hold. Yes. But can you don't be shy? So everybody gets a gift. Yes. Okay. That's right. Or you can also unwrap it.
It's a picture of him singing. Go home. Oh.
So this is a bit of a history book by now, turns out. So I read this book a few years ago, and of course we know much more about this question now than we did a bit more than 20 years ago. But when I read it a couple of years ago, I found it extremely interesting how in some areas of science, The aliens were here, yes. Some areas of science we actually know much more than when this book was written, but in some areas actually we don't. And this book, I think, while it's a popular science book and not a scientific article, I think it has changed or has impacted the way we think and approach these questions substantially. And I think that many of the ways we look at present day at exoplanets are still shaped by some of the thoughts that were expressed in this book. So in case you get the time to read it, I think it's really worth it because it makes us understand, or at least it made me understand the way we approach these questions today. So now let's thank the LOC again.
All right, little intermission before we go ahead. As the LOC, thank you again for all the applause. But you might as well have figured it out by now that at the LOC meetings, there was one name and mostly one name next to 90% of the tasks, and it was Tim Lichtenberg. So it may look from outside that he's a great boss, and that is the truth. So all together, we wanted to give a little something to Tim, which could not be more contemporary, if you will, please. And this is also from the SOC, of course. And yeah, so again, thank you, Tim, from the LOC and the SOC.
Actually, we have one final gift for our boss. Yeah, so yeah, exactly. This is not for your pub quiz skills, but rather for your organization skills. Thank you so much, Tim, for everything.
Thank you very much. All right, can we take a picture? Can we go together? So many emotions. Yeah, thank you so much. Okay. Okay. We're nearly there. Breakout sessions, I think, were an integral part. And so I think also that led to many interesting discussion. I think when I attended the past few Rocky Worlds conferences, the breakout sessions are really important for getting to know each other, to have a purpose to talk each other, not just awkwardly walk to the senior person, say, hey, cool, your science is cool, can you talk to me, please? So I think these are really integral, and I think they make the Rocky Worlds conference series special in the way they make us interact with each other. So thank you to the breakout session organizers, hosts, for making this possible. Now we nearly have it. Now, yeah. So this is the fourth installment of the Rocky Worlds conference series. The first one was organized in Cambridge 2020 by Amy and Ollie, who just left the room actually, and many others, of course. And the second one, I helped organize this conference with also many people at the UK and the University of Oxford. The third one's organized mainly by Paolo Sossi, who is here, maybe still in the room. I don't know. No, he left as well. Like this, yeah, and many people at ETH Zurich. This event was organized by this LOC and the SOC, and the question then becomes, what's happening next? Excitement, yeah. Ooh. Guess what it is? Guess where it is? Who can understand where it is? And there we go.
So this was already a preview for the pub quiz that we're going to have in 2 years. No, but we are extremely proud and happy to organize the next Rocky Worlds conference in Berlin, in Germany, in this extremely colorful, diverse, vibrant city. And we needed to convince the Rocky Worlds team quite a bit. Also go for a very bold, neon, colorful style, which you can read in the spectra of an atmosphere or something like this in there. We actually even have a bouncing atmosphere. So this is actually how in 2 years we all feel like the beating heart of the city, the beating heart of Rocky Worlds will be in Berlin. And since the city is most beautiful and colorful in springtime, we actually suggest to move it a little bit later than usually. So the meeting will take place from the 3rd to the 7th of April at also university campus, very similar setting as we have now in Groningen this year. And so we are still looking at exciting venues, evening, potential public outreach events, things like that. Stay tuned for it. The website, the skeleton website, is already up. And there's a possibility to sign up for getting announcements for the Rocky Words 5 conference. And you can also see here the rough timeline that we plan for the next 2 years. So we hope to see most of you, maybe even all of you, and bring more people along in 2 years in Berlin.
We very much look forward to it. Thank you so much, Lena. So we hope to see you all in 2028. And this is even thinking further ahead. We have this nice color palette there. So far, there has been no formal process to essentially decide where the next Rocky Words conference will be, and we thought we tried to be as open as possible essentially on all these conferences, and we thought the allocation of this should also go this way. So we decided to formalize this process a bit more. It's not supposed to be complicated, but it's supposed to give everybody the chance who wants to essentially host this event. And so what we will do, we will announce this sometime in early 2027, essentially, just on the website, on the rockywords.org website. We open essentially proposals for Rocky Words 6, yes. Then after the Berlin event, essentially. It's not supposed to be long. Whoever wants to host this event should send us like a roughly 2-page description with some description essentially that should be included so that it follows essentially the spirit of the Rocky Words conferences. And then the board of the Rocky Words discussion series will discuss this and then reach out to people who propose to essentially host the event. And so if you follow any of our mailing lists, you will hear about it and we will announce it on the website. And really, finally, we are there. This is it. I think I will leave up this slide. There's now lunch outside. Please, for those of you who have still posters on the poster boards, please take them off and enjoy lunch. Thank you again for this event and have a very good travel home. Thank you.